Hey there, I'm here, the tutor, Sam. I wanted to make sure we cover all the topics needed for our journey towards the education of mathematics and physics and all the science-related topics that is covered even in the uni. So what I could share is I got my expertise in math and physics and some other topics, and even in the first year or the fresh year or the sophomore, you're gonna have to go through these topics one by one, which is not very hard, actually pretty simple, and I'm gonna make it simpler. It's a pretty big topic, pretty long topic. It's gonna take a while. It's gonna take a very long while to cover all these topics together, but if we do it together, we can definitely do it in short time. So one course is called Calculus and Linear Algebra. So it has a lot of topics. I'm assuming we have the basic knowledge of calculus, basic knowledge of linear algebra, how the differentiation and integration works, and the linear algebra, which starts from the algebraic equation to different lines and vectors and matrices, and furthermore from those topics. Functions is a pretty important part of linear algebra. So what are you going to do in this topic? You're going to cover the final part of calculus and linear algebra, because calculus is a vast topic. There's a primary part and there's main part. The primary part is for the elementary knowledge, which I assume we all have that. If we don't have it, then we're going to go through that another day to cover all those topics, and those are gonna be the basic structure of the calculus and linear algebra. I know we all can do that. So today we're gonna go through the second topic, the main topic, the in-depth, the main calculus and linear algebra, which starts from function, and from function I can go from different topics to topics. So we're going to go through all of them together one by one. Let's start with function. What is a function? We all know what a function is. So f of x equals x plus blah blah blah. Yeah, what I put here is the domain. What we exactly get here, all the elements are called codomain. It's a very basic structure, guys, and it's just still part of the first year matrices and function and linear algebra. And the possible codomains, all possible elements of codomain is called range. Say the range can be from x number to y number, or minus x to plus x, from different, sorry, it can be all numbers in real numbers, but x or y or some specific values. So you're gonna get to that all one by one. So we're gonna revise our basic knowledge in function. So the topics you're gonna go through little by little is limits, the squeeze principle, which is very, very easy and fun topic. It's fun to learn that and fun to go through that. It's fun to teach as well. Continuity, when a function is continuous, the intermediate value theorem, which suggests that if there is two function points, then in between them there might be a certain point, there should be a certain point which gives you a zero value, or which gives you the value that you should have as an average. And then we're going to go to a differentiation, which is the basic one. Nothing interesting about it. So if you go through limits, a limit is a value that a function approaches L when the input of the function approaches a particular value. So, say we have function, particular function approaches a value called a, so it is the input, which is the domain of the function, reaches a particular value a, then a function approaches L, so it could be from negative side of a, or it could be from positive side of a, and we could reach either L or a different value. So when we are saying the negative side of a, which means number smaller than a, that's what we mean by negative a. And if we take this as an input, then we get a particular value as an output. And if we take this as an input, which is number larger than a, then we get a particular value. If both value goes towards L, then the limit exists. The limit of f of x tends to n negative, which is this negative smaller value than a. That means when the f of x approaches a from a smaller point towards a, and there's another limit f of x approaches a but from a larger point towards a, and we both have an output for both limits. This will give us an output, this will give us an output. So we're going to come to the point. The limit of a function f of x as x approaches a is described by limit x tends to a, f of x equals L. That's our output. Limits are useful for examining the behavior of functions and identifying properties such as asymptotes. If you wanna, in a graph, you sometimes wanna go towards asymptotes. So, what asymptote says? That a number reaches towards 0. It could be an x-axis or it could be in a y-axis or infinity. This in this case is infinity or reaches towards 0. Then that is our asymptote, and in that case we can measure that using our limits, right? So that's why limits is very important. Limits are useful for examining the asymptotes and many other important topics, and we're going to know about this all step by step. So left and right hand limits, let's study a bit thoroughly about this. Left and right hand limit. Left and right hand limits allow us to state the direction in which to approach the limiting value, right? A left hand limit approaches the limiting value from numbers smaller than what I just said. So if this is a in the number line, so all the numbers in here that approaches towards a, so this is the negative part of a, this is the smaller part, and this is the smaller part, this is the larger part of it. I mean large by this, small by this. So all the numbers that approaches in here is negative, a negative, and all the numbers that approaches to a from the right side is a positive. So a left-hand limit approaches the limit value from number smaller than the limiting value. In this case, we will write this by limit x tends to a negative f of x. And the right limit approaches the limiting value from the larger than the limiting value, which is from the right side. So vice versa, limit x tends to a positive f of x. And so left and right hand limits are not equal. Normally, the left hand limit and the right limit are equal. Say if both are equal L, then the limit exists. But if the left hand limit and right hand is not equal to right hand limit, then the limit does not exist. We have to remember that. Then there are several techniques we can use to evaluate limits. The techniques we choose depends on the given function. So one technique is direct substitution, which is the basic form of finding out the limits for functions which are defined at the limiting value. Limit x tends to 1. Say we take an example. For an example, limit x tends to 1, x squared plus 2. What is going to give? So if x tends to 1, then if you put the value 1 here, it's going to give 2. It's going to give 1 and plus 2 equals 3. So it's just nothing. And there's another example we can give. Limit x tends to 4. 1 by x plus 4. In this particular case, x is going to be 4. We're going to get a 1 by 8. So just substitute. It's like plus or minus or just do it. Or multiplication or division. And there's another form called factorization. In this case, we're going to cancel out some forms. When a function can be factorized to cancel out undefined terms. Say if limit x tends to 2, and we have an example of, say, x squared minus thrice x plus 2 by x minus 2. So in this case, if we put 2 in here, we're going to get some value, but if we put 2 in here, then we're going to get 0 in our denominator, which is going to be very, very complicated. It's going to get to infinity, it's undefined, so we're going to try to avoid that by factorizing. So what we're going to do, which is also very basic structure, we're going to take x squared minus twice x minus x plus 2 by x minus 2, which is going to be x minus 2, x minus 2, x minus 1 by x minus 2. In this case, we can factorize this form and we have x minus 1 left. 2 minus 1 is going to be 1. A very simple method. Then we've got conjugation. Can apply when a function involves square roots. Say we got limit x tends to 2 root over x plus 7 minus 3 by x minus 2. In this case, we try to avoid the square roots. So how we can do that? We're going to take the opposite, the conjugate square root in both numerator and denominator. And numerator and denominator, and then it's going to be root over x plus 7 minus 3 by x minus 2 into root over x plus 7 plus 3 and root over x plus 7 plus 3. In this case, we're going to get, since 2, it's going to give us x plus 7 minus 9 by x minus 2 root over x plus 7 plus 3. And in this case, x plus 7 minus 9 is going to be x minus 2. In this case, this and this cancels out. We have only this left, which if we put the limiting value in there, we're going to get 1 by root over 2 plus 7 plus 3. X is 2. Okay. Yeah, we already got that. We already put the value in. The answer is going to be 1 by 3. So the main structure is we use a conjugate square roots to cancel out a few terms and see the terms cancel out, and we don't have that form anymore. and the important part, we skipped 0 at the bottom, at the denominator. So we have already gone through the basic ways of solving limits. Now, next part we've got limits to infinity. This is a very, very fun part. Can apply when the limit extends to infinity and the function involves power of x. Sometimes we have got power of x like limit like 3x to the power 4 plus twice x plus 7 by 2x power 4 plus 3x cubed plus 4x squared plus 9x plus 7. We can make it big, it doesn't matter. In this case, what we can do when the limit x tends to infinity, we're going to divide all the numerator and denominator by the highest power. So if we divide all the elements by x to the power 4, we get 3 by 2 by x cubed plus 7 by x to the power 4 by 2 plus 3 by x plus 4 by x squared plus 9 by x cubed plus 10 by x to the power 4. And this is what's going to happen as x tends to infinity. X to the power 2 tends to infinity. X to the power 3 tends to infinity. And of course, x tends to infinity. So when you divide a number by infinity, x by infinity, or y by infinity, the number becomes 0. So all the numbers in here and in here become 0. Because we are dividing all the elements by either x or x squared or x cubed or x to the power 4. Then we're dividing all the elements by infinity, and then we get output of 0 in all these elements. So we are literally canceling out all these elements. We have the highest powers left. So the answer is going to be 3 by 2. Very simple. Then the squeeze principle. One of the most fun part. And here, for your practice, to practice at your time and comfort, I'm giving some problems. Limit x tends to 1 by root over 3x plus 6. Limit x tends to 2, x squared minus 3x plus 2 by x minus 1. Do this at your time, at your free time. It's a practice problem for 1 plus. Like, you can also find a lot of practice problems are out there. You can just find it and solve it. So I'm going to go to the next topic, the squeeze principle. So what is the squeeze principle? The squeeze principle says it's just like squeezing, or you can call it a sandwich principle. So we have got something in between our sandwich or our burger. There are the buns or crusts on top and bottom and something in between. And when we say that, say this is a number level, what is x or y axis? It's a number graph and Cartesian graph, and this is y-axis. So this point we say 1, this point is say 2, this point is say 3. So what the squeeze principle or the sandwich or the burger principle, anything you can call it, says is that normally what we see, if we can take that if we consider all of them as a line or as a point, and they all have similar distance from each other, that says 1 for this example, then this point in y direction is 1. The patty is in the point 2, and the third bun is, and the second bun is point 3. So in any case, if the first bun, top bun, and the bottom bun are in the same point called 2, in that case, where is the patty? Definitely in 2. There's no other bun or patty. Everything's single line. That's what squeeze principle says. If the 1 and 3 becomes 2, the same number, then where would the patty go? Patty has nowhere to go. It has to stay in the middle. So the number from 2, which is greater than 2, are equal, and also less than 2 are equal. What is it? 2. There's only one number. That's what squeeze principle says. So they just make a random thing saying f of x and g of x and h of x. So h of x is greater than equal f of x and less than equal g of x. In case f of x equals 2 and g of x is also equals 2, so h of x is greater than or equal to, okay, we still don't know, it might be equal to or greater than, and also less than or equal to, then there's only number 2. That's it. That's squeeze principle. That's it, guys, you're done. I don't know why people make it complicated. So when a function is bounded above and below, above and below, we can apply the squeeze principle. That is, f of x is greater than or equal to g of x and less than or equals h of x for all x close to the limiting value a. Okay, so limit x tends to a, g of x equals L, and same for h of x equals L. Then in that case, f of x can only be one value, which is L. So what is the number that is greater than or equal L and also less than or equal L? L. Doesn't make sense. And then why the minute topic is everyone knows it already. So we can solve problems through the squeeze principle. So let's go to an example. Let's calculate this limit. It extends to 0 x sine 1 by x, 1 by x. Since we know that sine 1 by x, any sine value can only range from -1 to 1, we can determine bounding functions by multiplying x. So if we multiply x in this equation or in this line, we get -1 negative x, x and 1 by x, and positive x for x is greater than 0. Alright, for x is less than 0, it's going to be the same. The sign is going to be the opposite. So we've got that the g of x, or the g of x, the function that we're trying to get, is gonna be G of x is a lower limit. There's a lower limit and there's an upper limit. So G of x is the lower limit. So G of x is going to be minus x for x is greater than 0. For x is greater than 0. And positive x for opposite. H of x is going to be positive x for x is greater than 0. And negative x for opposite. What does it mean? So there can be only one solution to that. Right? So we're saying for x greater than 0, g of x is greater than 0, and h of x needs to be negative x is positive x. Alright? And if x is negative, as our x is valid for both negative and positive numbers, it's the real number. So for a negative, the g of x turns to x, like positive x. So what's the number between minus average number between, or what's the mid number between negative and positive x? 0. And what's the summation of negative x of positive 0? So gain is the squeeze principle, is a number from 0 greater than or equal to 0 and less than or equal to 0, so the number is 0. And the use of bottom functions are limit x tends to 0, g of x equals limit x tends to 0, h of x equals limit x tends to 0, f of x equals 0. Let's go to the next topic. Alright, you can solve another. Oh, no, we didn't give enough. So, what it says, x sine x, x sine 1 by x in this particular is greater than or equal to g of x and less than or equals h of x. So, taking the limit of the above equation gives limit x tends to 0, x sine 1 by x is greater than or equal to g of x and less than or equal to h of x is greater than or equal minus greater than or equal to 0 and less than or equal to 0, so the number is 0. You can do some practices. It's pretty simple. Alright, I think we've done enough. Squeeze principle, which is the most basic principle. I've given the basic structure and the basic knowledge and understanding of squeeze principle at the beginning of the example. So there's not much to learn about this. So when a number is between a lower limit to a higher limit and the lower and the higher is the same, then say x can be minimum 2 and maximum 2. So what is x? 2. That's what squeeze principle is. Let's go to continuity, which is another very, very, very basic. So what we're doing here is we're revising function. We all know about it. We're revising limits. We all know about it. So the function below is continuous. We can show that. Let's give an example. F of x equals 5 if x equals 1, and 2x plus 3 if x is not equal to 1. So we must show that limit x tends to 1 of f of x equals f of 1. Otherwise, it wouldn't be continuous. So what it means, we draw a function here. We draw a line. So this is f of x, and this is the graph of f of x, line of f of x. This point is f of 1. All right. So this is the x-axis. this is 1, this is 2, this is 3. So this point is f of 1. When it be continuous, when we approach to 1 from a number smaller than 1, the function is continuous, and when we approach to 1, when the function is smaller than 1, the function is still continuous, like we are getting values close and close to f of 1. So in this case, what needs to be done? When x tends to 1, which is very close to 1, it needs to be equal to f of 1. Evaluating the limit gives that limit x tends to 1 f of x equals limit x tends to 1 2x plus 3, which is 5, which is f of 1, so it is continuous. Alright, so actually the graph for this particular function f of x equals 2x plus 3 for x not equal 1 is gonna look something like this. This is a straight line. You all know the graph of straight line. It's gonna go through the y-axis for the number 3, and its tangent is gonna be 2. Slope is gonna be 2. So it's very simple. We just need to practice. And then a little bit more in continuity. So you've got an example of if x equals 3 minus x, if x is less than or equal to 0, and x squared plus c for x is greater than 0. So we require the limit of the function exists as x tends to c. Right? When x tends to c, we know that the limit exists, which means the left hand and the right hand limit should be similar. So what we mean by that, limit x tends to 0 plus f of x equals limit x tends to 0 negative f of x. Evaluating a limit gives limit x tends to 0 positive x squared plus c equals limit x tends to 0 negative 3 minus x. So in this case, c equals 3. So the limit exists. The function is continuous. We can write this thing. For our next, we call it intermediate. So that was all for continuity. Our left and right limit should be equal, and it all should come towards the same point. When the x value tends to a certain value, which should be the exact number of when x tends to y value, then it should be the certain number of when you input y, the number we get. When you input x, we should get the same output. That's what it says. That's continuity is. Next topic, we are coming the intermediate value theorem, IVD. All right, pretty chill. That's it. A perfect circle. We get it. Intermediate value theorem. So what it says, we should use all the tech to improve our learning that makes our learning much faster, fun, and much quicker, simpler. And we want to learn that. We are more interested in learning that topic. So let's make it easy and fun. Let f be, so in intermediate value theorem, we take a function f be a continuous function on the interval a to b, which means a and b included, such that if a to b interval tends to r, all of them are real numbers, then for every point c between f of a and f of b, so for every point c, we call all of them c, not all of them, there exists an input x between a and b such that f of x, there is minimum one point where f of x equals c. So how do we graphically show that? So this is our, let's make it a bit better. The graph, completely good looking graph. And this is our graph. So we call this f of a is this point, and this is f of b, this is f of b, this is our b, this is our a, this is a, this is b, this is f of a, this is f of b. So there is at least one point for x. So if we put f of x, so the x is here, then the f of x is here, this is f of x, it should be c. Alright, very simple. This is f of x. Remember, this is f of x equals c. So that's what we went through in the beginning. The intermediate value theorem is particularly useful for determining if a function crosses the x-axis. So still, it didn't cross the x-axis. And if f is a continuous function on the interval a to b, and f of a and f of b have opposite signs, then there is a point x between a and b such that f of x equals 0. Why? Because f of a is negative and f of b is positive. That means there is something in between for any x value that we get all the points inside and we draw a function. This is f of a and this is f of b. There are infinity amount of points in here, and for each point there is an input. We get all these infinity amount of points as output. So there's always infinity amount of values to get this infinite amount of points. So of course between negative and positive there's a number which is 0, is this point. So there is a value we can put to get this point 0. That's what it's saying. So if this is f of a and this is like this is a, this is f of the, this is f of a, and say this is b, this f of b, this is b, and this is f of b, then there is this point which is 0. which was caused by f of x. That's continuity. That's intermediate value theorem. So, which also very much precisely makes sure that the continuity is occurring in all these functions. All functions are continuous. If this weren't continuous, there might be a certain point that the function could go like this, and this, and our y-axis in between. If the function is not continuous, then it's actually, we're not getting it. It is continuous, and then we make sure that the function is continuous through the intermediate value theorem. Let's go to another one. Show that the function, let's use an example. Let's show that the function has a root between 1 and 2. Between 1 and 2. So, function is x squared minus 2. So when we put f of 1, we get negative 1. And when we get f of 2, we get 2. So we definitely have something in between that gives us f x equals 0. By the IVD, in fact, here there is a point x element of 1, 2, like from 1 to 2, there is a point such that f of x equals 0. That's our solution. And that's pretty simple. And let's use another example. Show the equation has a solution between 0 and 1. Okay, between 0 and 1. The equation is e power minus x equal x. So we take e power minus x as a function of x, e power minus x. So as f is continuous, you can apply the intermediate value theorem in here that says, so the interval is 0 to 1. F of 0 is going to be 1 minus 0. And f of 1 is going to be 1 by e, or e power negative 1, which is less than 1. So in this particular solution, therefore the IVD, there exists point x element of 0 to 1 such that f of x equals 0, and hence the equation has a solution between 0 and 1. So that's our intermediate value theorem. And we come to differentiation, which is, again, one of the most interesting topic that we have done in calculus for a very long time, and we're going to do the differentiation through the function to the limit, which is the basic way of solving differentiations. So the instantaneous rate of change or derivative of function f at the point x equals a is given by the limit f prime a equals limit h tends to 0 f of a plus h minus f of a by h. If above limit exists, then we say that the function is differentiable at the point x equals a. Note that this approach is differentiation is referred to as the first principle. So let's go to an example. F of x equals x squared plus 3. So f prime x we can write limit. We all know the solution is twice x, but we can solve this with the limit function theorem. In that case, limit h tends to 0, f of x plus h minus of x by h. So it's x plus h, or x is quite similar, x plus h and x quite similar because h tends to 0, so we can assume h is 0. In that case, x is just x. So in this particular solution, we'll limit h tends to 0, f of x is actually x squared plus 3, so if x plus h is x plus h whole squared plus 3 minus x squared minus 3 by h. In this case, we get on top, what do you get? H tends to 0, x squared plus 2xh plus h squared plus 3 minus x squared minus 3. So by h. So in this case, we get 2xh plus h squared by h when limit h tends to 0. So we get h tends to 0 to x plus h, and we get 2x. So that's pretty similar, pretty simple method to solve it. And we can use the same thing, and there's a alrighty. So if we go for continuation on functions, there is a few other topics we're going to go through in this lecture, and it's going to be L'Hopital's rule. I used to call it something different, like when I was younger, like literally when I first started, I was like, okay, hospital, but it's not hospital, like just look at it, it's L, because he's French, his name is Lo, his name starts with Lo or something. Yes, there's a lot of French scientists out there who invented a lot of great solutions to finding out the solve for math equations or physics, or mostly math equations, integration calculus, and Mr. L'Hopital is one of them. And his name is not Hospital, his name is L'Hopital. And L'Hopital's rule says very easy thing that when a function is in a form of undefined form, says 0 of course at the denominator, and the 0 is also on the numerator. So the numerator and denominator both has 0, or they both has infinity, so 0 over 0, infinity over infinity, or undefined terms like this, then we can use L'Hopital's rule to find the limit of this. So we're going to go to that topic. So what do we do actually if we take the limit of x tends to 0 and do x squared plus sine x? In this case, we can solve it. But if we use the L'Hopital's rule, what are we going to do? We're going to differentiate the numerator, and we're also going to differentiate the denominator. So if we differentiate the differentiation of x squared is twice x, and the difference of sine x is going to be cosine x. And in this case, we get limit x tends to 0 twice x by cosine x. Cosine of 0 is 1, and this is 0, so we're going to get 0 for this solution. if we took x by sine x, where limit x tends to 0, then we actually get 0 by 0, but we shouldn't get something like this. So we use L'Hopital's rule to differentiate both the terms. The difference of x is 1, sine x is cosine x. In this case, we can write this limit is equal to 0, 1 by cosine x. And cosine x equals, cosine 0 is 1, so 1 by 1 equals 1. So in this way we can say limit x tends to 0, sine x by x equals x by sine x, same thing. And few other topics that turns 1. And we're gonna come to the point slowly. So we're gonna learn more in depth about L'Hopital's rule and a little bit of MVT and Rolle's theorem. So MVT stands for mean value theorem. RT is like Rolle's theorem. There's another scientist, Rolle's, that came up in this regard and tried to solve the equation. And the integral to infinity. So we're gonna solve all of them step by step. Let's go to L'Hopital's rule. L'Hopital's rule is a very useful tool for evaluating limits which involve quotients. So we have x by y, and both of them are either 0, it could be 0 by 0, it could be 6 by y equals 0 by 0, or 0 by infinity, or infinity by 0, or infinity by infinity, or there are a few other terms we have, which like all these terms actually are very unhelpful towards solving math equations. It's not just undefined, it's just undefined. You can't even find any values for this. So in this case, we use L'Hopital's rule. It states that under certain conditions, the limit remains unchanged after differentiating both numerator, in here is x, and denominator, which is y in here, of quotient. And suppose that f and g are differentiable functions around the point x equals a, and we can say limit x tends to a f of x equal limit x tends to a g of x equals 0, or plus minus infinity, or it can be both. Alright, or it can be 0 infinity or infinity 0. So in this case, what I can do, then I already showed you the way of solving the problems. Limit x tends to a, which is differentiate both the numerator and numerator and denominator. So f of x by g of x equals limit x tends to a. F prime is a differentiated form of f(x), which is the differentiating value in g prime x. So we took the sine example long time ago. We say sine x by x is, in here sine 0 0, x is 0, we get 0 by 0, but we shouldn't get something like this. So what do we do? We use L'Hopital's rule, and we can put it as sine x. If we do differentiating, cosine x and x turns 1, cosine 0 1, that's it. Now we go towards MVT, which is mean value theorem of this form. So what does the mean value theorem says? If f is a continuous, if f, the function, is continuous on the interval, again, we take 2 points a and b, and let's do the graphing. Graphing makes our understanding much easier and simpler. So if there is a graph like this, then say this is f of a and this is our a value, which is in x-axis. These are x-axis, these are y-axis. This is gonna be f of a, and this is another point b. This is f of b. Oh, it's not quite parallel, but we assume that's parallel. This point b in x-axis, and for b, the function would be this as the point in here. So for this point, we can say what is the rise of a run. If this was a between f of a and f of b, if this was a straight line, this is the rise of a run. This is the tangent and or the slope from point f and f of b. This was a straight line, then there is at least one point between a and b for which the slope is going to be similar. So for this, we can say this one's quite, it's not quite exactly. Okay, we assume that in this point we have the similar slope. So this point is occurred by a point C in x-axis. So for f of c, we can say that f prime c equals f of b minus f of a by b minus a, which is going to be the rise or run, which is the slope. So if f is continuous in the interval a to b and differentiable on ab, we just show that, then there is at least one number c such that in a, between a and b, such that f prime c equals if is a rise or run. So there is a, just like this slope, there's another slope in here in that function for any point of a and b. So the mean value theorem can be used to guarantee that a function derivative takes on a particular value given on the endpoints. This is particularly useful in design of air speed cameras. So what happens in a speed camera? So like if you're going, so this is in x-axis, again we draw the function. It's x-axis and y-axis. Say for x is the towards x-axis, we count the speed, and this is the time. So for it's the time, or we can use time for y direction in this case. So say for some point you're, oh, we actually, let's do this to, this is time in x-axis and speed in y-axis. So just like that, we can draw a graph like this. So the time goes in this direction, in x direction. So our speed was high, very high at the beginning of that journey, and then the speed was going down, and at some points it was even, speed cannot be negative. We're just assuming it's just a function that this is the 0 point, or this is the minimum point, and then at some points our speed again went up. We can easily, so if this is the average speed, we can say there is a function c. So this is a point, this b, this is f of a, this is f of b. There is point C for which the slope is going to be the same for this slope, and this is going to be the average speed. So this probably is in the design of average speed cameras. All right, very simple thing. The speed cameras work. How the speed cameras? So within a time interval 5 seconds, we're not supposed to go through, say, 30 kilo or meter per second, or probably like that's pretty much 5 meters per second, or say 2 meters per second. In that case, could be able to say that if a person was going in very small speed at the beginning and very high speed at the end, then the average speed still like crossing 1 meter per second, which is like actually crossing the limit the speed cameras were following. You should be crossing 1 meter per second. So that's how the speed cameras work. So even if you do not cross something very slowly, say the speed camera is in here, and you're passing the speed camera from A to B, and if the speed camera like determines speed from the path A to B and not just here, you're probably thinking, okay, I'm gonna go fast in here and go slow, and I can't go fast in here, so I'm not gonna know. But if the speed camera is determining the path from A to B, so it's gonna do the average, and yeah, you're still crossing the limit for the speed of that particular place. So that's how the speed cameras work. Rolle's theorem, pretty interesting topic and simple topic too. Describes if f is a continuous function on the interval, again it be and differentiable on a to B, then if f of A, which I just showed, I guess, equals f of B, then there is a point C in A to B such that f prime C, if we differentiate that, we get 0. So this is our y-axis, this is our x-axis, and we again take a function, say we can take this function, okay, we put it up for a bit and say this is f of A, this point, and this point is f of B. So this is A, this is B, okay, and if f of A is so, which means they both have the similar y value or y-axis value, then there is this point C, which is mostly in the middle of the completely symmetric graph. Okay, we take this as f prime C equals 0. C as that is f prime C. If we do the differentiation of the graph, it's going to be 0 because it's completely horizontal towards like from y, horizontal vertical to y, and horizontal from x-axis is going to be 0. So it's like very simple. And if we even if we take a example like this, even in this case, f of A and f of B is similar because here C, A is a negative value, but B is a positive value. But for this function, f of B is a positive number, f of A is a positive number, and they both are similar. Okay, so for this, there is a point C such that, let's write a bit better. I just went a bit farther. Let's go close to it. Okay, let's say goes through this point, and this is C, this is f prime C, is gonna be 0 for f of c. This is f of c, and the f prime c is 0 as it's horizontal to x-axis. That's all 0. That's very damn simple. Nothing to worry about it. And we just don't know like why people try to make this a little bit harder in the exams and tests, saying that the Rolle's theorem are not very easy to solve. But see, we just find it out that we just take a differentiation of points and we get 0, and that's Rolle's theorem. That's it. As simple as 0. It's like binaries, so like simple numbers. Rolle's theorem can be used to define whether or not a function has a stationary point with a given. So in this particular example, okay, this is a stationary point. So we are going to like if this x-axis is the speed, so speed is going down and then speed is going up. So at some point the car was stationary. Speed is going down. That means or the acceleration is stationary. There's an acceleration. So the first acceleration is going down, negative acceleration, and the acceleration is going up, positive acceleration. Some points, acceleration is 0. Okay, we get some stationary point. That's what it means. Within a given interval. And let's say f of x equals x minus 1 whole square plus 2, extension point in the interval of minus 2 to 4. Okay, because f of minus 2 is gonna be 11, and f of 4 is gonna be 11. That's it. So f prime, so equineural so there has to be a point c such that f prime c, if we take the differentiation of c point, we get 0 in interval of minus 2 to 4. So combined with IVT, invariant value theorem, Rolle's theorem can also be used to determine whether a function contains only one root within a given interval. So, for example, we can show that the function has only one root in the, say, we take an example f of x for x plus x minus 3, since f of 0 is less than 0, and f of 3 is greater than 0. By the invariant value, there's a point c in c as if like like f of c equals 0. So let's assume there's a point d. It's just f of d equals 0. So like there's only one point, like say from 0 to 3 we're counting in here, which can give 0. So f of c should be equal f of d. There's no c and d. There's the same points equal 0. So by f of c equals f of d 0, so there is a point s between c and d such that, so like if c and is a different point, d is a different point, and both equals 0, there is another point f of y equals 0. Like, what can I say? So this should be a topic for primary level, like literally for kids. Everyone's kids, like until literally for like preschool kids, I'll say. So it's as simple topic as that. So nothing to learn much from there. So we all should just grudge it. Then we come to the point that the derivative function f of x would be f prime x, it's e power x plus 1. The function was e power x plus x minus 3, which is there is x by x plus 1, is greater than 0, because it can't be a negative, and there's a positive number. So for all points in the interval 0 to 3, that contradicts rule 0. So the assumption that there is a second point D, the rules like theorem says there's only should be greater than 0. So there's no such thing as equal 0 or less. So the assumption that there is a second point D such that f of D equals 0 is incorrect. Therefore, the function has only one root, and which is c, and that is f of c equals 0 in the interval 0 to 3. So from IVD, we can, using Rolle's theorem, we can say that there is only one root for the solution. Alright, integral. The integral to infinity. Integrating the integral to infinity gives, so 1 to infinity, f of x dx equals limit m tends to infinity, f of x 1 to m. Alright, so for example, well, 1 to infinity, integration 1 by n squared dn, the result is going to be 1 by n squared is n prime minus 2. The integration is going to be n prime minus 2 plus 1 by minus 2 plus 1 is going to be n prime minus 1 minus, which is going to be minus 1 by n, and go limit m tends to infinity minus 1 by n 1 to m means infinity. So say the answer is going to be 1, because if you divide something by infinity 0, the negative 1 is infinity, is 1. What I'm saying. So I was going through a lot of topics together, covering a lot of topics together, so it was going through a little bit hard for covering all of them together. So alright, let's go to another big major topic, which is gonna be a very major thing for learning at some points in our linear algebra, and that is sequences and series. Alright, so we're gonna cover intro to sequence, arithmetic, and geometric sequences, and arithmetic and geometric series. So this is just a sum of sequences, nothing different, nothing very different. And then we're going to have infinite series, so that keeps going towards infinity. Then we'll have term test. It's pretty simple. Comparison test. We have infinite geometry series, which is a geometric series, but it goes to infinite. We're going to do sum, we're going to find a value in the middle. And then we have got p-series test. And we've got harmonic series. Alright, what is a harmonic series? Say a series like 1 by 2 plus 1 by 3 plus 1 by 4. See, it's going forward harmonically. So we call a harmonic series like 1 by n plus 1 by n plus 1 plus 1 by n plus 2, just like that. So let's come to introduction. Introduction to sequences. A sequence is literal. So what is sequence? So say I write 1, 4, 9, 25. So 1 is the square of 1, 4 is the square of 2, 9 is the square of 3, 5 is the square of, put 16, right? Square of 4, square of 5. So can we record it? So what is it? This is a sequence. We write all numbers together. The numbers together. It's actually a sequence of n square, where n starts from 1. So 1 square 1, 4, 9, 25. It goes on. So this is a sequence. I can write this. Say a sub n is the nth element of the sequence, as if it's part of natural number minus 0 goes to C. Alright, we didn't write C properly. We can write it like this, where n is 1, 2, 3, 4. That's what n is, and it keeps going. For example, the sequence has a rule: a sub n equals n square. Okay. Alrighty. Well, sequence has a dependent variable. Often, n, their elements are represented as a n, then keeping n together as a sub n. For example, a sub n or n sub n equals n plus 1, or b sub n. So it's for n plus 1 is gonna be 1. So if this n starts from 0, 1, 2, 3, n starts from 1, 2, 3, 4, and continues. And so b sub n, say n plus 1 divided by n squared plus n plus 5. And then c sub n equals logarithm of n by n factorial. So the two most common sequences are arithmetic and geometric sequences. Alright, so let's come to an arithmetic sequence. So if we write 1, 2, 3, 4, and on, we can see it's just increased by 1. So each time it's increasing by 1. Or we can write like say 9, 8, 7, 6, and it keeps going. Each time we are decreasing by 1 again, but it's increasing or decreasing by a single value. So in this case, we're going to call it an arithmetic, or we can give it like say 9, 6, 3, 0, of course comma in the middle, -3, it keeps going. So each time it decreases by 3, so like the difference, so from second term and the first term, if we do substitution, is -3. So arithmetic sequence means when the sequence increases or decreases by a single value, by a fixed value. And what geometric sequence means, so we can write 1, 2, 4, 8, 16. So each time actually it's not increasing, it's not increasing, it's multiplying. So in here it's multiplication of 2 becomes 2. Again it multiplies with 2, 4 times 2, 8 times 2, 16. So it's not increasing, it's multiplying by 2. Same like that, you can write 16, 8, 4, 2, and on. And each time it's dividing itself by 2. So a bit clear. So like in both cases, it's either multiplying or dividing. So that's what geometric sequence, when it multiplies or divides itself, if it increases or decreases, that's arithmetic. So it's very simple. When the series comes, we keep adding all the elements of the sequence, and then we come to a term. We can come to a sum, or we can come to certain other topics. We're going to come to that. So that's what arithmetic and geometric sequence is. And arithmetic sequence is a list of numbers with the difference between neighboring terms same. For example, we've just given an example where each term increases by a single number or decreases by a single number. We can write this. So we can write this with this form, in this form. A sub n equals a, which is the first term, plus d, which is a difference, n minus 1. So if we write 1, 3, if we write 0, 2, 4, 6, so second term a2 is going to be a0 plus difference is 2, and n minus 1 is going to be 1. 2 times 1. So the second term is 2. Okay. So we write it. A sub n equals a plus n minus 1 into d. And for this one, right, the second term, it's a ratio, we can call it. For multiplication, the ratio is 2. For division, the ratio is half, or 1 divided by 2. So the ratio is the first term is a, and n is the number of the term, of the term. In this case, it's r to the power n. All right. If n equals 2, then a r to the power 2. If r is 2, 2 squared 4, a, which is 1. And the second term is 4. So it's just, we can write a sub n, which nth term is a, h is the first term, r ratio to the power n. Where n equals 1, 2, 3, and on. Very, very, very simple and similar and very easy fun. I remember doing that, or most of the people might have done this as a kid when you used to solve problems. But we never really went through forms, like a general form, like a formula, or like we didn't use and errors. We know that, okay, 1, 2, 4. We did that when we were a kid, right? We didn't use a form. So there's nothing to learn, new to learn in here. We'll have to create new formulas, and this is part of second series. So we have learned second series as a kid. So you can understand how that is. We learned as a kid. Nothing much to take in here. So any problems comes regarding second series, we're gonna be able to solve like that. We're gonna be able to solve that easily in the test. or nothing much to do about it. Then convergence, and so the sequence and series has both two characteristics. What's sequence in here? Convergence and divergence. So what is convergence? A sequence is to be converged if the limit, say n tends to infinity, n equals L, exists. Say when the number tends to infinity, and still we can find the limit of that nth term, of the infinite term exists. So if we go towards infinity and still we know a number, then the sequence is said to converge. Right? That's converging means going down or coming to a certain point. Diverging is from a certain point is spreading over. So that's how this is the time x-axis, and this is the measurement for spreading. Then it's spreading away or spreading or still going on. So spreading, that is divergence. And if it's coming to a certain point, that is convergence. Alright. If the limit doesn't exist, then it diverges. For example, s of n equals 1 by n. If n tends to infinity, then s of n tends to 0. So it converges. Alright? And b sub n equals twice n. If n tends to infinity, then b sub n tends to twice of infinity, which is infinity, so it diverges. Alright? So, second example, a sub n equals, say, n squared plus thrice n minus 1 by n squared minus 4n plus 2. So if we take the limit n tends to infinity, a sub n is going to be, so we have done the solution, only the highest power remains, is 1. So the limit exists and the sequence converges. But say take another example where say n cubed, we took 1 extra power plus 2n squared plus 3 by 4n squared or 5n squared plus 4. All this will cancel out when limit n tends to infinity. We try to take f sub n is gonna be, we're gonna divide that by n squared, so we'll have n left, which is infinity. So it's gonna be diverge. It's diverging. So it's divergence. So we can easily solve like problems from there. Let's come to series. Okay, series is some of particular number of terms from a sequence, and like so sum n equals 1 to n. N could be a certain value. It could be infinity. It could end at any, like n could be like say first 10 terms, the summation of first 10 terms, or summation of first 20 or 30 terms, or could be infinity of a sub n of that sequence. So a sub n is a sequence, and n is the final term, is the end term, and n equals 1 is the starting term. Okay, so for example, say summation n equals 1 to 5, twice n is gonna be, so it starts with 1, twice 2 times 1 is 2, so 2 plus 4 plus 6 plus, it's an arithmetic series, plus 8 plus 10 this is equals 30. So this is a series. This is a summation of the series. So we can find this in different ways. An arithmetic series is self-terms in an arithmetic sequence. All right. For example, we can write summation, give a better summation, n equals 1 to 5, 1 plus 3 into n minus 1. Okay, so for n equals 1, the first term is going to be, for n equals 1, is going to be 1. For n equals 2, so it's going to be 4. Alright, and 7, it keeps going on. Equals 1 plus 4 plus 7 plus 10, plus, as we take 5 terms in total, so 35 is the summation of the series. Okay, in general, the truncated sum are, so in general, in truncated sum, which means easy way to getting that sum of an arithmetic series, n equals a plus n minus 1 into d is the summation of n equals 0 to say k. N, so like k is a number from 0 to 0, 1, 2, 3, like natural number, is k by 2 a plus a sub k. A sub k by 2. Alright, so what it means, the summation is going to be, S of n is going to be, say we've got n terms, n by 2, first and last term. Alright, when n is the number of terms, we like to sum, and that's it. Geometric series is a sum of terms in a geometric sequence. For example, summation of n equals 1 to 5 to the power n, like 2 plus 4 plus 8, blah blah blah, is 160, whatever, is the geometric series. We already know what geometric series is, so we can write in this formula, shortened way. Summation is going to be a into 1 minus r to the power n by 1 minus r, when r is much less than 1. So when r is much less than 1, or n tends to infinity, then we can say that r to the power n almost equal to 0. In that case, the formula that becomes Sn equals a by 1 minus r. Alright, and in this case, r is not equals 1. Otherwise, it's gonna be just, there's nothing. Alright, when n is the number of terms, we like to sum. N is the first term, so this is where we're getting Sn equals a into 1 minus r to the power n by 1 minus r. If r is less than 1 and n tends to infinity, then the Sn equals a by 1 minus r. Okay. Infinite series is self-infinitely many terms. Summation n equals 1 to infinity. So we come to the so we come to the topic infinite. series, which is a sum of infinitely many terms. So when n equals 1, first, second, third, it keeps going towards infinity, 1 to infinity, n equals a1 plus a2 plus, it keeps going towards infinity. Since infinity series at infinitely many terms, it's interesting to determine whether the results in a number, any particular number, or tends to infinity, or are not defined. All right, so we have to get that. So a series which results in a number is a convergent series. Because we're adding infinitely many terms and still coming to a certain number. That means the series is converging. Okay, it's a convergent series. And a series which is not convergent is called a divergent series. All right, so this is very, very easy. The term test says that there are many different tests which can be used to determine whether a series converges or diverges. Okay, the term test allows us to determine if a series diverges. Okay, that's what we're looking for. The term test states that the series summation n equals 1 to infinity a sub n diverges if limit n tends to infinity a sub n is not equal to 0. All right. Note that if the limit equals to 0, so if the limit is not equal to 0, if the limit has a value which can be negative or positive, so it's like if the limit is not equal to 0, then the series diverges. Okay, so what if a series is equal to 0? Well, then we don't know if it diverges or if it doesn't diverge. All right, so we can use a few examples. Summation for each of n equals 1 to infinity. Summation n equals 1 to infinity, 1 by n squared. So in here, if limit tends to infinity, 1 by n squared is going to be 0. So we don't know if the series, what happens to the series. And if, for this case, if we take 1 plus n squared by n squared, which is actually going to be when the limit n tends to infinity, we know the highest power cancels out by 0, so 1 left, so 1 number, and it's not equal to 0, so it definitely diverges. Not equal to 0 diverges, and we can come to this n squared plus n cubed by n squared minus 1. So we'll have n left tends to infinity, so which is again not equal to 0, and it's going towards infinity, so it definitely diverges. So that's how we know how if the series diverges. If the limit tends to infinity, not equal to 0, diverges. Okay. could do a few more examples. I think the examples are good enough. Again, I'm gonna recap. See, the limit is 0, so we don't know if it's converging or diverging or what's happening. We don't know through the term test. If the limit equals 1, it's not equal to 0, so it diverges. If it's not equal to 0, it diverges. Infinity, it definitely diverges. Okay, it's not equal to 0, it's not 0. Infinity, so it's definitely diverging. It's diverging. Or we can say again, not equal 0, so diverges. The comparison test. Comparison test. When we do comparison test, what happens? We should know some particular series, the infinite geometric series and the p-series test. What's a p-series test? P-series is, we take p as a power of something. So an infinite geometric series, summation n equals 0 to infinity, it's a geometric series. R to the power n, like would converges when the ratio r is less than, the modulus of r is less than 1, and otherwise diverges. Otherwise, right? Because otherwise the numbers keep getting up, and if you keep adding it towards infinity, it's gonna go infinity. Like the numbers, the n term is gonna be infinity, so it's definitely diverging. So only when the ratio is less than 1, or even the negative, like the modulus ratio is less than 1, then the number will keep getting lower. I mean, less than 1, or less than, or greater than minus. So in that case, it converges. Diverges otherwise. Example. So we take summation n equals 0 to infinity. Phi is the first term. A. Ratio is 1 by third. And we're going to get the n terms. So as ratio is less than 1, it converges. Alright. And to the n, so a is 1, ratio is 2, it diverges. Ratio is greater than 1, it diverges. Okay? It's very simple. The p-series test. The p-series test. The p-series test states that the series summation n equals 1 to infinity 1 by n power p, so p is power, converges, remember it converges when p is greater than 1. Okay, in that case, denominator keeps increasing, and at some point when the term is in some infinite term is going to be 0, or like with a very high number it's going to be 0. So it's going to be a converging series, and vice versa, diverges when p is less than or equal 1. Okay. Example. Give an example. 1 summation n equals 1 to infinity 1 by n squared. So p is greater than 1. So it converges. Okay. converges. Okay, and summation n equals 1 to infinity 1 by n p power 1, which is less than or equal 1, so it diverges. Alright, it diverges. Because it's gonna keep getting up, not that much, which is gonna be 1 by 1 plus 1 by 2 plus 1 by 3 in arithmetic and geometric way, something similar. So yeah, it's definitely diverging. Okay, not actually towards arithmetic, we're doing completely in general form, so it's not a good example to give instantly, but we know when we have the power of 1, then it's definitely diverging, and if the power is greater than 1, then it's converging. Alright, okay, let's go to this one. Summation n equals 1 to infinity 1 by n. Oh yes, right, it's power 1, so it's diverging. Right, so we can write 1 plus 1 by 2 plus 1 by 3 plus, right, you can keep going, so it's gonna be a diverging series. Diverges. And we'll soon prove that this diverges. So just hold on, sit tight. We're gonna get there soon. The harmonic series, I already gave harmonic series. It's the most harmonious looking series. The harmonic series says that the series summation n equals 1 to infinity 1 by n. So 1 by 1 plus 1 by 2 plus 1 by 3 plus, it keeps going on and on. So you'll see, like, the numbers like 1 half, 1/3, 1/4, 1/5. So that's how it's adding up. So that's what is a harmonic series. It's a harmonic series. It's referred to as a harmonic series. Harmonic series is a divergent series because the power is 1, and if the power is less than or equal 1, then it is a diverging. Too much of the convergence divergence. We are just getting too much pumped up in here. It's pretty useful series to remember, as we can use to show that. Yeah. Okay, so we have few more topics, things to do for series, which is gonna be comparison test, limit comparison test, and ratio test to cover in series. Alright, with that, we're gonna be able to come to almost to an end. So, the comparison test. Sure, it's very important. The comparison test show the series converges. Okay, so summation n equals 1 to infinity 1 by n squared plus n plus 5. So in this case, we must show that the sequence in the series is smaller. So this is smaller than 1 by n squared plus n, and that's smaller than 1 by n squared. And with the p series, we can see that this is converges. Alright, so this is definitely a convergent series. Again, summation n equals 1 to infinity n plus 5 by n squared, which is bigger. So this is bigger than n by n squared, or we can call it 1 by n. It's in here the power 1. It diverges. So in here we got something, okay, and a smaller series is converging. The bigger, this is bigger than this one. Bigger series is converging. This is the smaller one, definitely converges. Here, the smaller one diverges, the bigger one definitely diverges. Alright. The limit comparison test. Use a limit comparison test to determine whether the series will converge or diverge. The series is summation n equals 1 to infinity n squared minus 5 by n cubed plus n plus 2. First we must find a sequence to compare against. So we can compare this with 1 by n, because when n tends to infinity, this and this all goes down. Okay, this one goes down to when we this one is like 1. No, this one actually have 1 here. So when we have n, when we divide by n squared in both numerator and denominator. As n tends to infinity. Therefore, possible choices. Okay, b sub n is 1 by n. Okay, so now calculating the limit gives. So b sub n is a comparing series. Now calculating the limit gives limit n tends to infinity a sub n b sub n, hey there, equals limit n tends to infinity n squared. So at first we write a sub n squared minus 5 by n cubed plus n plus 2 divided by 1 by n, which is going to be into n. Okay, so it's going to be then n tends to infinity n cubed minus 5n by n cubed plus n plus 2. Alright, in that case, like it's gonna be 1 when n tends to infinity. Right? So since we found that a sub n by b sub n equals 1 is greater than 0, and since summation n equals 1 to infinity, b sub n equals summation n equals 1 to infinity 1 by n. So 1 by n is like power 1, so it diverges. We can conclude that by the limit comparison test that the first series also diverges. Alright, so let's come to the worked of limit convergence test to determine whether the series will converge or diverge. So we have n equals 1 to infinity, and got here 2n squared minus 3 by 3n to the power 4 plus n squared plus 2. So we can literally compare this with, so b sub n is going to be 2 by 3n squared, and when you do a sub n by b sub n, we're going to be actually multiplying with the opposite, so it's going to be 3n squared by 2. So 2 is not going to make much difference. So when you come to this point, it's going to be 6 in power 6 in power 4 by again 6 by 6 in power 4. We're going to have that left, so we're going to have 1 left. Okay, and this one has got power 2 converges, so we also take bn is 1 by n squared. That's quite fine, and in that case it's gonna be 2 by 3, which is greater than 1, right? And also it's the power is 2, so it's convergent. All right, so we can say that our first series also converges. Very simple. All right, the ratio test. The ratio test is a ratio test to determine if the series converges. Okay, so we've got summation n equals 1 to infinity 1 by 6 power 2n. Right, so we can calculate the limits. Gonna be, we can write this thing into 1 by 6 squared to the power n, because 1 to the power n is gonna be 1. All right, so we can calculate the limit r equals r is a ratio n by n plus 1 by n limit to infinity, then limit to infinity. It's gonna be 1 by 6 for n plus 1 is going to be 6 to n plus 1, and 6 to n is going to be 1 by 6 squares at the end. Is a ratio which is less than 1. So the series, if the ratio is less than 1, the series converges. After some topics, we come to an example to work out the ratio test to determine if the series converges. So n by n factorial. Okay. So summation n equals 1 to infinity. So you can easily see n by n factorial is like gonna be n, and it's gonna be n into n minus 1 factorial. So 1 by n minus 1 factorial. All right, and when we do that to get the ratio is n plus 1 by s of n is going to be 1 by n factorial by 1 by n minus 1 factorial. Can write that as n minus 1 factorial by n factorial It's also going to be into n-1 factorial, and n-1 factorial cancel out 1 by n. Alright. So in terms of n tends to infinity, 1 by n tends to 0. Now since r is less than 1, the series converges by the ratio. It's actually turns 0, and the second term is going to be 0 all over. So a few other things we need to learn that covers the root test, integral test, alternating series, alternating series when you have -1 power n, then the sign changes. The first term sign is positive, then negative, and then again positive, then negative. And the integral test, we use integration, and the root test is we are covering up. The root test states that if n is a sequence and r equals limit n tends to infinity, in power 1 by n, then this series converges. If r, so 1 by n, this means actually root, right? 1 by 2, power 1 by 2 means root over, power 1 by 3 means cube root of something. So if r is less than 1, then it converges, and if r is greater than 1, then it diverges. Alright, pretty simple. Note that if r equals 1, for the root test, if r equals 1, we cannot really come to a conclusion. It's gonna be, we cannot say that this is diverging or this is converging. So for the root test, let's use an example. 2 power n by n plus 1 power n. Here r equals n tends to infinity, a sub n power 1 by n. So it's gonna go to the power n by n plus 1 power n. We go whole power 1 by n, so it cancels out. Cubed by n plus 1. If n goes to infinity, then it goes to 0. So it's inconclusive. We don't know if it's diverging or converging. So r is less than 0. It's inconclusive. If r is greater than 0, then it's divergent. Less than 0 is convergent. So it's inconclusive. And the series convergence, let's do this one. To the power n by n plus 1 to the power n. If we put root in here, n root, we get 2 by n plus 1. In any case, it says since state 0, and r is less than 1. Convergence by root test. Wait. So for root test, if r equals 1, it becomes inconclusive. Okay. If r is less than 1, it's convergent. If r is greater than 1, it's divergent. So for 0, r is less than 1 is convergent. Very simple. Let's go to integral test. You used to say that if f of n equals a sub n is a positive decreasing function, then if integration of k to infinity of f of n dn converges, then summation n equals k to infinity and converges. Okay, it's pretty much like similar. And if integration of k to infinity f of n dn diverges, then summation n equals k to infinity diverges. Alright, so whether this is useful when the sequence, whether this test is useful when the sequence n can be easily integrated. Okay, the integral test, use the integral test to determine if the series. Let's do an example. Summation n equals 1 to infinity 1 by n. So if we do integration of 1 by n, we get log n, right? So log n from 1 to infinity. So if log infinity, therefore log infinity is like infinity. So therefore, since the integral diverges, the series also diverges by the integral test, and then summation equals 1 to infinity 1 by n squared. Integration 1 by n squared dn is going to be minus 1 by n. 1 to infinity is going to be, if you put infinity, is going to get 0. If you put 1, then minus 1 is going to be plus 1, so it's going to be 1. Okay, so the integrals coming to a certain value, so the integral converges. The series also converges. By the integral test. Alrighty, so we were at the integral test, and we saw if we can find a limit from the integral test that it converges. Then the alternating series test. The alternating series test. An alternating series is a series in which each term alternates between positive and negative values. Okay, so minus 1 to n, then it's going to be negative, and then the positive, the next term is negative, and the next term is positive. So alternating series is a series in which term alternates between positive and negative values. In general, alternating series has the form summation n equals 0 to infinity minus 1 to the power n, or we can have also sine or cosine pi. Sine pi is 0. Cosine pi alternates from negative to positive 1. Sine it is like n of pi by 2. Oscillates from positive to negative 1 as well. And for this one, actually is enough to know that the value alternates from negative to positive. And in that case, we go from s sub n is a series, and some is supposed to include, say, such n equals 0 to infinity minus 1 power n by n square. So minus 1 power n is for the alternation, and so the series is 1 by n square. So from the P series, we see that it's actually known as a convergent series, and there is the alternating values as well. So a few other alternating series example is such an equals 1 to infinity minus half power n. So I see. Show you how this works. So we can write it minus 1 power n into minus 1 by n power n minus. Or we can just make it plus 1 power n and 1 by n power n. Also, you can write such n equals 1 to infinity cos n pi by n. The cos n pi is an alternating series which comes from negative 1 to positive 1. And there's n. Okay, the alternating series states that an alternating series summation n equals 0 to infinity minus 1 power n sub n converges if a sub n is a positive sequence, or a sub n is greater than 0, or a sub n is a decreasing sequence, that means a sub n is greater than the next term, or a sub n converges. Decreasing sequence, or positive sequence is greater than 0, or a sub n converges to 0, which is most of the things that happens like 0. Suppose limit n tends to infinity and 0 equals 0. So from there we can go to an example. The example is n equals 1 to infinity minus 1 per n. 1 by n has n tends to infinity, limit n tends to infinity, 1 by n it could be 0, so it's a convergent series. We want to make sure it's clear that for n equals greater than 1 by n it's definitely got to be greater than 0. So it's a positive sequence. And also 1 by n is greater than the next one, so it's decreasing. And yeah, at some points it turns 0. So everything just takes to the point that the series converges. The 3 points says that the series converges. Okay, so for example, just use one example. So there are a few other examples. We can try that later. We can try that in time. There are several different types of convergence for. So this is one thing. Types of convergence. There's several different types of convergence for series. However, focus on two. One is absolute convergence, and the other is conditional convergence. Conditional convergence is something that there is a condition applied to the convergence of the series of sequence. So absolute convergence means that an infinite series is an absolute convergent. An infinite series. If both summation equals 1 to infinity a sub n and summation n equals 1 to infinity modulus of a sub n converge, then of course it's an absolute convergence. Conditional convergence is an infinite series is conditionally convergent if summation equals 1 to infinity a by a sub n converges, but there's a but if its negative value, say summation n equals 1 to infinity a sub n modulus diverges. Okay, if it's a negative value could diverge, while the other converges and the negative diverges. So that case is a conditional convergence. Okay. Now, here's an example. Summation n equals 1 to infinity minus 1 power n 1 by n. So, from the previous discussion, we can say, does a by n converges? I think the power 1 it does not, but it's an alternating series, so it's positive. It converges. If it's greater than the next term, if it's decreasing, it converges, and if it's 0, it converges. It's not 0 in this case, but tends to infinity. At some points 0, it converges. What about you take the whole thing as a modulus? What's going to happen? Then this is going to be look, earlier you saw that the series convergence is the alternating series test. Since after using the modulus, this actually cancels out and the series diverges. And this is actually conditional convergence. Conditional convergence. Alrighty. The next word. During the type of convergence. Convergence of the series. Okay, summation n equals 1 to infinity minus 1 power n, 1 by n squared. So what happens is a positive number and also decreases and also times 0, it converges. Okay. Now, if we put a modulus in here, this goes out and we have still converges, so it's absolute convergence. All right, absolute convergence. Beautiful. And from there we go to the next topic. It's called the P series, so it's absolute convergence happening. Absolute convergence. All right. So next, there's still things to do, and we're still at series. At this point, we do this one. Power series. So the topics we're gonna go through is introduction to power series. Differentiating and integrating the power series, which is gonna be very cool. Differentiating and integrating. We're gonna find some cool solutions there. Then comes the convergence of power series. Convergence of power series. Power series like basic P series we already solved it, and power series is coming up. Radius of convergence. Radius of convergence for the power series. And interval of convergence. Interval of convergence. Okay, so let's go to power series. What is a power series? Power series, all right? Okay, a power series is a series which is dependent on the powers of a variable. Now, in general, a power series has a form summation n equals 0 to infinity a sub n x minus x naught power n equals a naught plus a1 x minus x naught 1 plus a2 x minus x naught power 2, and on and on. Now, where x represents the dependent variable, x represents the dependent variable, and x naught a number, which is referred to as the center of the power series. Okay, note that x can represent a complex number. X can definitely represent a complex number. Now, with power series, I say many functions that we're familiar with can be represented by power series. These are called power series expansions. For example, e to the x exponential function is, we can write as 1 plus x plus x squared by 2 phi plus on and on equals summation equals n equals 0 to infinity, and we can call it x to the power n by n phi. Okay, x to the power n by n phi, and sine x we can write as x minus x cubed by 3 phi plus x power 5 by 5 phi minus, this is all taking series, on and on. So we can write it as summation n equals 0 to infinity x by 2n plus 1 by 2n plus 1 whole phi. Okay, cos x equals 1 minus x squared by 2 phi plus x power 4 by 4 phi minus blah blah. We can do summation n equals 0 to infinity minus 1 power n. This is the alternate series. There's an alternate series as well, and of course give me something. There's definitely, if it's an alternate series, there's minus 1 power n, and x power twice it by twice n phi. And with the series below and series below in form. So normally the form is like this: summation n equals 0 to infinity a sub n x minus x naught to the power n. Okay, so power series. Any continuous series can be differentiated or integrated to that. Any continuous power series can be differentiated or integrated term by term. So differentiation is going to go like, for the differentiation, dx of summation n equals 0 to infinity a sub n x minus x naught power n. It's coming from there. Okay, so summation n equals 0 to infinity a sub n x minus x minus x naught power n is going to be equal to summation n equals 0 to infinity a sub n into n x power, oh yeah, this is the integration form, x minus x for n minus 1 x minus x power x naught power n minus 1, and integration we put as integration of summation n equals 0 to infinity a sub n x minus x naught power n dx. It's going to be summation n equals 0 to infinity. You know, like how the integration works. Say so instead of x minus x naught power n plus 1 by n plus 1. And we can differentiate or integrate the known power series of a function to differentiate or integrate the known power series of a function to generate the power series. integrate the known power series already. So when, for example, we see summation n equals 0 to infinity x power n, it's going to be equals 1 by 1 minus x, and we can differentially integrate to find that 1 by 1 minus x squared is equal, there is a negative sign here, equals summation n equals 0 to infinity, and actually we're n minus 1. So we're n minus 1. So we can write from there, taking log or something like that. There's a differentiation part. Alright, there's a differentiation. There's also an integration part. With the integration, we can see that, well, we know 1 minus x, 1 by something. If we do that, we get natural log, or 1 minus x equals summation n equals 0 to infinity x to the n plus 1 by n plus 1. So, by differentiating the power series, expansion of sine x, we can do this. dx of sine x equals cos x. We can just differentiate the power series expansion of sine x. We can show that differentiation of sine x cosine x. And remember, sine x has got a series. It's got a alternating infinity series, which is summation equals 0 to infinity minus 1 per n x power 2n plus 1 by twice n plus 1 whole phi, by integrating the power series expansion of cosine x. We can also show that integration of cosine x dx is gonna be sine. It's actually minus sine, minus sine, but it's an alternate series. Something we're gonna find sine x plus c. So remember that cos x has got an infinite alternating series, which is n equals 0 to infinity, minus 1 power n for alternating, and x power twice n by twice n phi, and convergence of power series. Now we come to convergence of power series. Convergence of power series. So applying the ratio test to the series, we can use n equals 0 to infinity a sub n x minus x naught power n. Applying the ratio test to the series, we can this will give us r equals limit n tends to infinity a sub n plus 1 x minus x naught powers n plus 1 by a power n a sub n x minus x naught power n. So what happens, this completely goes off and we have power 1 left over here, into this one. So we can write x minus x naught modulus limit n tends to infinity a sub n plus 1 by a sub n, right? Okay, that's our convergence of power series. Okay, a7 plus 1 by 7. Then the ratio test state that the series will converge whenever r is gonna be less than 1. So r equals x minus x naught, limit n tends to infinity, a7 plus 1 by a7 is less than 1. There are three possibilities. In here scenario. What are the possibilities? The limit diverges. Okay, if the limit diverges or doesn't exist, if the limit diverges or doesn't exist, the series diverges for. If the limit diverges or doesn't exist, the series diverges for all x. If the limit converges, the limit converges to 0. If the limit converges to 0, the series converges for all x. Series converges for all x. And if the limit converges to a non-zero number, if it converges to a non-zero number L, the series converges within some interval of convergence. Converges within some interval of convergence. Okay, our next topic goes to when the limit converges to a non-zero number. So when a limit converges to a non-zero number L, we can determine an interval of convergence. Okay, we can determine interval of convergence. X minus x naught modulus into L is less than 1, where x minus x naught is less than 1 by L. Here 1 by L is referred to as the radius of convergence. This 1 by L is referred to as this is the radius of convergence. You need to remember this. The interval of convergence then minus 1 by L plus x naught is less than x is less than 1 by L plus x naught. So we use an example. The interval of convergence for the series. We need to find out the interval of convergence for the series. Summation n equals 1 to infinity x power n by 6 power 2n. You can say 6 squared power n. the series will converge for r equals less than 1. Let's see if the series converges. You write that in here, actually we can see you can write that it's like x by 6 squared per n. X is the thing that comes forward. This is going to be the ratio per n. Going to be the ratio. So the ratio is 1 by 6 squared equals 1 by 36, which is less than 1. So, substituting the result gives x modulus 1 by 36 is less than 1. Therefore, the series converges provided that x modulus is less than 36. And thus we can write x is from the range of minus 36 to 36, given the interval of convergence for the series. So the interval of convergence is, for in this particular case, minus 36 to 36. Given the interval of convergence for this series. Okay, another series we're getting on with. Again, we can see x minus 2 is coming in, and the limit for r equals x minus 2 into limit tends to infinity, blah blah, which is going to be x minus 2 into 1 by n squared, 1 by 6 squared, which is definitely going to be 1 by 36 into x minus 2, so less than 1. So given the interval of convergence of the series, so therefore the series will converge provided that x minus 2 should be less than 36. And we can say x minus 2 should be minus 36 to 36. So we had plus 2, minus 34, 38. There goes our x minus 2. That's for the interval of convergence for this one. Let's do another example. Summation n equals 1 to infinity. N plus 3 by n phi power x to the power n. Alright, so x to the power n stays almost, and so in this case, we have to see that n plus 3 by n phi into x to the power n. Right. So what we have to do in this case, the limit gives limit n tends to infinity s of n plus 1 by s of n, limit n tends to infinity gives us n plus 4 by n plus 1 phi, and x power n, we're going to separate it, and if we the opposite is going to be n phi by n plus 3. So at the end we're going to have 0. Okay, 3 into n plus 1. So we got a double power at the denominator. That means if the n tends to infinity, if we divide by n, then over we got something and on the numerator, and the denominator got 0, which means so the highest square is n squared. So this one is 0 and this one is 1. So we'll have 0 at the end. Therefore, the series converges. So the series converges. Then we can do a little bit of practice and voila, we got another one. This one is called Taylor series, and in here the things we're going to cover is intro to Taylor series, Taylor polynomial, Maclaurin series, Now, I'm going to cover all these topics. The series, the polynomial, and Maclaurin series. Step by step. So we saw that the function we are most familiar with can be represented as power series. Okay? For example, for x equals 1 plus x plus x squared by 2 phi plus blah blah, we can say summation n equals 0 to infinity x to the power n by n phi, and then sine x equals x minus x cubed by 3 phi plus x power 5 by 5 phi minus something and blah blah blah. So we can write as summation n equals 0 to infinity x to the power 2n plus 1 by 2n plus 1 whole phi. And for cos x, it's a bit easy. It's 1 minus x squared by 2 phi plus, there's minus 1 power n in the beginning. This is alternating series plus 4 by 4 phi minus 6. It keeps going, so we can say summation n equals 0 to infinity minus 1 power n and x power twice n by x power twice n by twice n phi. So the Taylor series of a function f of x, the Taylor series of a function f of x is a power series expansion. Of the function expansion of f of x about a center x naught. So f of x equals f of x naught plus f prime x naught x minus x naught, which we're just making another series, and if double prime x naught by 2 phi, oh my god, it's a pretty big series. If double prime x naught by 2 phi, x minus x naught square, and plus f triple prime x naught by 3 phi, x minus x naught cube plus going on. So we can write that as summation n equals 0 to infinity f n power function of x naught by n phi and x minus x naught power n. This is referred to as the Taylor series expansion. Taylor series expansion. Of the function f of x about x equals x naught. We also have to note that in tech and everything, we also have to know that the Taylor series expansion of the function may not converge. Okay, the Taylor series may not converge. Sequence and series. Note that the Taylor series may not converge. We have to make sure the rest of the series and the rest of the solutions are complete uniform. A special case of the Taylor series occurs when x not equals 0. A special case. X not equals 0. And f of x not equals 0, and f of x equals f of 0 plus f prime 0 x plus f del prime 0 by 2 phi x squared plus f triple prime 0 3 phi x cubed plus on and on. This is a special case when x not equals 0, then we can write summation n equals 0 to infinity f of n of 0 by n phi into x power n. Phi into x power n. So this series, in that case, in the special case when x not equals 0, we can write it like this, and voila, we got Maclaurin. See, we're jumping from topic to topic, so Maclaurin series. So the Taylor series itself was a very good understanding because we already had the previous series of different known functions turning into infinite series, and we can make it to a sum, and then we can say it's a power series, it's a Taylor series by adding the differentiation of f prime, double prime, triple prime, and yeah, it's an nth function. And when that case, x minus x naught, if x not equals 0, then we can just have x, and that's enough, and we have our Maclaurin series. This series is called the Maclaurin series. A Taylor polynomial of degree n. Taylor polynomial of degree n is a Taylor series up until the Taylor series up until the nth power. Up until the nth power. So Taylor polynomial dnx and x naught plus f prime f x naught plus f prime x naught x minus x naught plus if double prime x naught by 2 phi into x minus x naught power 2 plus blah blah blah, and f of n power x naught by n phi by x minus x naught power n, and we can write as summation n equals 0, k equals, because that's we're writing k equals 0 to n, f of k of x naught by k factorial it's like we were saying that n equals 0 to infinity, or 0 to number is equals 0 to, whereas towards n, the final is n, and then 0 1 2 towards n. So k factorial by into x minus x naught power k. Okay, so the Taylor polynomials the Taylor polynomials are particularly useful. Polynomials are particularly useful and we do the best possible solutions. Particularly useful for approximating the value. Of the functions. For example, t1x would provide a linear. For example, t1x would provide a linear approximation to the function. Then, for example, show me a Taylor polynomial of degree 3. Degree n, we got degree 3 in here. Around the center, x equals 1. For the below function of x equals 4 e power 3x. The degree 3 Taylor polynomial has the form Tn of x equals f prime of 1 plus f of 1, there is nothing over there, f of 1 plus f prime 1 of x minus 1 plus f double prime 1 of 2 factorial x minus 1 square plus f 3 of 1 by 3 factorial x minus 1 cube. To determine the polynomial, to determine the Taylor polynomial, we must evaluate the first 3 derivatives at x equals 1. First 3 derivatives at x equals 1. So, working determining Taylor polynomial degree 3 around the center x equals 1 for the below function. Evaluating the first 2 derivative at x equals 1 gives f of x equals 4 e power thrice x equal, and f of 1 equals that, and f prime x equals 12 e power thrice x, and there's a f prime, and then there's f prime, and there's f double prime x x, and then there's f double prime x equals. So taking the first 2 derivatives, get the work to see. We have to determine the Taylor polynomial of degree 3, and the center x equals 1 for the function below. Substituting the derivatives into the telepolynomial gives t3 for the first 3 degree of x equals f of 1 plus f prime 1 x minus 1 f double prime 1 by 2 factorial x minus 1 square plus x triple prime 1 by 3 factorial x minus 1 cube for e cube plus 2 of e cube, what have we got, into x minus 1, and what have we got into x minus 1 whole square, and then what have we got into x minus 1 whole cube. Then whole cube. We can view how accurate the tail polynomial is by plotting both t3x and f of x. It's almost very accurate. So if we plot the graph, take a different color. This color is for the function, and this is for the Taylor polynomial. A little bit a little bit like this. So this is f of x. You can write it. This is f of x, and this is d3 first 3 degree of the Taylor polynomial. So it's pretty accurate. The plotting of the Taylor polynomial. Okay, as we increase the order, that was only d3. All right, as we increase the number, as we increase order of the Taylor polynomial, it becomes closer to the function. Taylor polynomial becomes closer to the function. We can take another graph. And let's check it out. Not exactly. And there is the graph. Almost similar. So we can see this is this is the f of x, and there's a Taylor polynomial. It's the 5th power, right? If we keep increasing, okay, then it's gonna exactly become more accurate. For the Taylor polynomial degree 3 of the function below, but the center x equals 0 is some example. So we have two functions here. X equals 2 e power 3x, and g of x equals sine twice x. And also, this point of degree 2, this is for degree 3. Degree 3, and for degree 2, Find the Taylor polynomial of degree 2 for the function below around the is degree 2 degree. Find the Taylor polynomial of 2 for the degree 2 for the function below around the center x equals pi. And we have to do this of x equals 2 sine x by 2, and g of x equals 4 cos twice x. And then we have to find it. Find the Taylor polynomial of degree 3 for the function below around the center x equals 0. H of x equals log 1 minus x. Z of x equals 1 by over 1 plus x. H of x log 1 minus x. Z of x equals 1 by over 1 plus x. Now, Taylor series appears everywhere in physics. They're often used to Taylor series appears everywhere in physics. They're often used to represent the solution of different equations. For example, the Helmholtz, the German guy, the German scientist, for electromagnetic wave, he did a lot of work regarding electromagnetic frequencies and electromagnetic induction as well, and his equation describes the propagation or the spreading of the electromagnetic wave through any medium, and he calculated that with Nebula square E equals epsilon mu del second partial derivative in respect of t of E. Thus the electromagnetic propagation through any medium is called Helmholtz equation. Alright. In 3 dimensions, this equation can be reduced into second order differential equation. In 3D, reduced into second order differential equation. Now, we've got once we have the solution in the form of a Taylor series, we efficiently approximate it with a Taylor polynomial. Solution in the form of a Taylor series, we efficiently approximate it with a Taylor polynomial r of r equals summation k equals 0 to n is k r power k. The degree of the Taylor polynomial will depend on the behavior. Will depend on the behavior of the expansion as well as the accuracy that we require. Such approximations are also frequently applied in physics, in particular when evaluating trigonometric functions. We use trigonometric functions in different cases and then we apply the Taylor polynomials. The small angle approximation is commonly used for the pendulum in physics in situations where cos or sine are evaluated for an angle theta when theta is much less than 1, or we can say that theta is much less than 1, and then almost 0.4 or less than that. Then we can use that in pendulums. Sine theta equals cos theta equals theta equals 1. Not 1, but it's equal, or yeah, something similar. The Taylor expansion of the sine function is sine theta equals theta minus theta cubed by 3 phi plus theta power 5 by 5 phi minus, it keeps going on. If the angle theta is much smaller than 1, if theta is much smaller than 1, the higher order terms in the expansion can be considered negligible. Okay? When theta is much smaller than 1, or even that many much is not needed, or even in this case, the higher order terms in the expansion can be considered negligible. In that case, sine theta is going to be equivalent to theta. Okay? Alrighty, so that's our power series and Taylor series and Maclaurin series and Taylor polynomial and Maclaurin series together that we had been using in our everyday maths and physics functions and infinite series and applications in different phenomena, physical phenomena included. We will discuss about the power series and the power about the Taylor series and the Taylor polynomials in details after. The more we solve examples, is much easier for us to remember the core value and solving methods. Also comes with the special case when x not equals 0, then comes. Otherwise, we can use Taylor polynomials in all the other infinite series and use it in different equations in physics as well. Yep. And with that, we finish for now the power series and the Taylor series, the Taylor polynomials. Preparing things, but the Taylor series is the thing that we finished very recently, and we also finished the Taylor polynomial Maclaurin series as well. We're gonna go back and do a bit of it later. For now, let's jump onto a little bit of a baby things that I've done in a chat as well, very long ago. So complex numbers, it's gonna be a revision. We're not gonna go through the whole topics in details because we already know what that is. It's a very important part of linear algebra. It's a basic of linear algebra. We can't even start linear algebra without having the basic knowledge of these topics. So complex numbers goes to topics of intro to complex numbers and arithmetic of complex number, arithmetic of complex numbers and complex plane, and complex plane. So if we go and do the introduction to complex numbers, in general, a complex number is a number which can be expressed in a form z equals a plus ib. I is imaginary number. I is equals root over minus, where both n be real numbers. N be real numbers, and I equals root over minus 1. Example, z equals 5 plus 9i, 3 plus 2i, and just like delta, and root 3 by 2 minus 1 by root 2y. We have often avoided calculation which involves square root of negative numbers, minus 1 or negative 4. We often had to avoid that. For example, when using the quadratic formula, x equals 4 plus minus root over minus 4. We had avoided those scenarios, but there's solutions. They're not real numbers, they're complex numbers. To write a solution, we can define a new kind of number, the imaginary number I equals root over minus 1. And we also write our solution in terms of I, and x equals becomes 4 plus minus 2i by 2. And if we do that, then it becomes 2 plus minus I. So now we have solutions that depend on I. These are complex numbers. Now, just like R denotes the set of real numbers, C denotes the set of all complex numbers. If we write is the set of all complex numbers, if we write Z element of C, it means that Z is a member of a set of complex numbers. And we have to know that the real number is a set of complex numbers. Now, arithmetic of complex numbers. Arithmetic of complex numbers. Okay. Complex numbers can be added, subtracted, and multiplied, almost exactly like real numbers. When adding or subtracting, we must separately add and subtract the real and imaginary part. So the real parts, we know the real part is the first part, and the imaginary part is the part with I. For example, 2 plus 3i minus 1 by root 2 minus root 3 by 2. 3, okay, equal, let's not give it a 3, let's 2 by 4, what number? Root 2i, just one, just enough. We can, the answer is gonna be 2 minus 1 by root 2 plus 3 plus root 2i. We added this and we added this. It's the arithmetic. Okay, another example, easy. 2 plus 3i plus 1 minus 4i. So plus sign is gonna be 3 minus I. So in multiplying complex numbers, we must remember I squared equals minus 1. So I cubed equals minus I. Okay, and I power 4 is gonna be, and I power 4 is gonna be minus 4 is gonna be I cube into I. Some I power 4 is nice. It's like I square. So it's 1. So it's like it goes through that. 1 minus 1 is I, 1, and pits. Period. It's a cycle of imaginary numbers. Period. 2 plus 3i for multiplication. 1 minus 4i equals 2 minus 8i plus 3i minus 12i squared is gonna be plus. So 12 to 14 is 8 minus 5i. Is that answer? We can solve more of them. So the absolute value of a complex number, the absolute value The absolute value of a complex number z equals a plus ib. And the capital absolute value of a complex number. So example ib is given z equals small is root over a squared plus b squared. It's also referred as modulus of the length of a complex number. So if z equals 6 plus 3i, absolute value would be root over 36 plus 9, 45 equals 5 times 9 equals 3 root 5. And also, you can take plus minus. We just took the positive, and z equals 5 minus 4i. Z modulus equals root over 25 plus 16, 35, 41. It's gonna be 41. Yeah, we cannot subtract. We can't simplify it anymore. So, is often real and imaginary parts of complex numbers. Real and imaginary part. Imaginary parts of complex number. Okay? Real and imaginary parts. It is often useful to extract. So z equals a plus ib. It's often useful to extract either the real or imaginary either real or imaginary part from a complex number. 500. It's only the real part, we just can write z equals a, and imaginary part equals b. And this doesn't extract the imaginary I, just extract the real number b, the real number v. B and the imaginary numbers, we don't bring that. And voila, we come to complex conjugates. Complex conjugates. Every complex number has a complex conjugate. Z equals a plus ib. A plus ib. Here comes the complex conjugate. To find the complex conjugate, we must simply change the sign of the imaginary number. So the conjugate form would be a minus ib. Complex conjugates can be used to generate many useful properties, such as z plus z bar. So we can write that as z bar as a complex conjugate. Z plus z bar equals 2 z plus z bar equals. We keep the conjugation rolling. 2 real power z, and z minus z bar equals 2i imaginary part of z, and z times z bar equals z squared, and z times z bar, this is the best. Z times z bar equals z squared, z middle square, and z plus w whole bar equals z bar plus w bar and z times w whole bar equals z bar times w bar. So rationalizing or the complex numbers. That was righty. Right. Oh, we didn't do that. Yeah, almost there. Rationalizing the complex number. Yeah, that's how I do it. We just don't make it 100% sure. Alrighty. So example. How to rationalize? Use complex conjugate. So an example is 4 plus 2i by 1 minus 3i. So we have got complex number in that denominator. So how to get rid of that? We're gonna multiply with the complex conjugate in both numerator and denominator. Then we find from there 4 plus 12i plus 2i plus 6i squared, so it's minus 6 by is and plus because of that, because of the I square. Okay, so first minus 2 and 14i by 10, so you can write as 7i minus 1 by 5. That's going to be the rationalizing form. Then can also have inverses. So if z equals a plus ib, z inverse equals 1 by a plus ib, and then z inverse equals 1 by a plus ib. So z equals 2 plus 5i, and then z inverse equals 1 by 2 plus 5i, and this is not a good form to keep complex number in the denominator. Then we do this, we use the complex conjugate, 2 minus 5i equals 2 minus I by just like that, 2 minus 5i by this is our inverse of the complex. Inverse. And then the complex number consists of real and imaginary parts. Complex plane. Complex plane. We can interpret complex numbers graphically in 2 dimensions. The horizontal axis is the real part, A, and the vertical axis represents the imaginary part of the complex number, that's B. And that's Z modulus. Imaginary part of the complex number. This is known as the Argand diagram, or the Argand diagram, or the complex plane. The complex number consists of real imaginary parts. You can interpret complex number graphically in 2 dimensions. When this is AB, is A, and is B, Z equals A plus IB. This is known as the Argand diagram. It's known as the Argand diagram, or the complex plane. Okay, so I got some few more topics now in this session. In this topic. So few more elements to cover from complex number. Is a polar form, Euler's form, or exponential form. Then comes De Moivre theorem. De Moivre, another Italian German. De Moivre theorem. And roots of unity. So, roots of unity, we're going to come to the point. Euler form is quite simple. Euler form is the simplest form of there. And there's some other theorem as well, including the De Moivre theorem. The Euler's form suggests us that using a little trigonometry, we can express complex numbers in terms of using a little using a little trigonometry. We can express the complex numbers in terms of their length and polar angle, right? Exactly. And in this case, if this is A, this is B, this is A, B, this is theta, this is R equals root over a square plus b square, z equals a plus ib, sine theta equals b by r, cos theta equals a by r, and tan theta equals b by a. That's theta, and that's trigonometry. We can got the compass plane. And the compass plane, this means that we have two ways of interpreting complex numbers: the Cartesian coordinates, and in terms of real and imaginary parts, real parts and imaginary parts. Z equals z a plus ib, polar coordinates, and polar coordinates in terms of the length of the number r, which is root over a square plus b square, and angle theta, which is tan inverse a by b, and z equals r cos theta plus I sin theta. We can write it also r cis theta. Now, the polar coordinates. Okay. You're gonna graph the below complex number, then express in z equals 1 plus root 3i. So if this is a graph, it's 1, and this is root 3. This is r. This is 1. This is root 3. R equals root over 1 plus 3 equals 2, and theta equals tan inverse root 3, which is pi by 3. So the form is z equals r cis theta equals 2 cis pi by 3. Now, for the polar coordinates, converting back to Cartesian coordinates is not a lot easier. So we know z equals r cis theta. Right, so r equals, all we have to do is evaluate cos theta and sin theta and expand the bracket. And much easier. For the previous form is to cis pi by 3 is going to be 2 cos theta. Cos pi by 3 is going to be root 3 by 2 plus I sine Well, wait. Cos pi by 3 equals half plus I sine pi by 3 equals 3 by 2 for the previous one. I'll go set up as theta. And then we can easily do it to 1 plus I root 3 or 1 plus root 3I. It's that simple. Pi by 6 and pi by 6, and even consider center from there. And there comes d mod is about the power. De Moivre's theorem alrighty. De Moivre theorem, which says that n equals r power n cos n theta plus I sine n theta, which we can write r power n cis n theta. For example, z power 10 is r power 10 cis 10 theta. Yep. And then comes Mr. Euler, the great Euler, to simplify everything. Euler's formula says z equals r cis theta equals r e power I theta. And in that case, e to the power n equals r to the power n cis n theta equals r to the power n e power I n theta. So same goes for the power. If the power is root, if the power is a quotient, then z power 1 by n equals r power 1 by n cis 1 by n theta equals r power 1 by n e power I 1 by n theta. So just in place of n is 1 by n. And then it folds up and complex solutions. And where are we? We just got the Euler's formula and then come to complex solutions. We now have all tools we need to start solving equations with complex solutions or root. So we can write that complex solutions, okay? It just doesn't stay aside. Solutions are roots. A regular polynomial of degree n has distinct solutions. However, we will sometimes ignore the solutions they were not real. For example, the equation z squared equals 1 has degree highest power of 2. We expect 2 solutions. By taking the square root of both sides, we find the solution z equals plus minus 1. If we treat z as a complex number, we can solve z squared equals 1 using a different approach. So z equals r e power I theta. this square equals r square e power I 2 theta. Now, this square equals 1. Let's not forget that, equals 1. Equals 1 into e power I 2n pi. And 2n pi or 2k pi is quite similar. So we're saying the value of this is 1 because 2n pi is going to be e to the power 2n pi theta into i's per I 2n pi is going to be 1. So we can write from here r equals 1 and 2 theta equals 2n pi. So theta equals n pi for n equals 1. Theta equals pi. N equals 2. Theta equals 2 pi. Theta equals 3. Equals 3 pi. So in that case, we can take the solution into now we know e power I theta equals 6 theta. From there we know e power so if theta equals pi, then 6 theta is going to be 1 because cos pi plus I sine pi is all 0. Cos theta and cos pi is going to be minus 1. So if we solve for, and also n equals 0, let's not forget 0. Theta equals 0. In that case, if theta equals 0, 6 theta equals 1, and then minus 1, and then 1, and then minus 1. So you can only see these two unique solutions, that is e equals 1 and minus 1. And that's our solution. Complex solutions. Graphically, what we have found are two solutions which are evenly spaced around complex plane. That's 1 and that's negative 1. And there is our z equals 1, z equals minus 1. That's our solution. We can repeat this approach on more complex. You can, for example, c cube equals 1. Now, equals, you can write r cube e power I 3 theta, right, equals 1 into e power I, again, 2n pi, right? So r equals 1, 3 theta equals 2n pi, theta equals n into 2 pi by 3. k, and for n equals 0, for n equals 0, we get 1. For n equals 0, for n equals 1, we get e power, for n equals 1, we get e power I so we can write the next form. Okay, so that's the solution for n. So the thing we're doing, theta equals n into 2 pi by 3. So if we put n equals to the first one, so first few, if n equals 0 is 1, if n equals 1, theta equals 2 pi by 3 e to the power I into 3. Or we can write that, so like we know, compare this with this, and compare this with this. Alright, to get the theta, and 2 pi by 3. So if n equals 0, n equals 0, theta equals 0. N equals 1, theta equals 2 pi by 3. If n equals 2, theta equals 4 pi by 3. And from there, you can write if theta equals 2 pi by 3, e to the power I theta is gonna be 6 theta equals 6 2 pi by 3. 6 2 pi by 3 equals, and it's cos 2 pi by 3, which is minus half, plus sine 2 pi by 3. It's gonna be 3 by 2. And r comes up in there. And I is there definitely. And if this is a solution, then another solution is going to come minus half minus I root 3 by 2. So that's the complex solutions. And graphically, if we want to put that into a graph, we're going to see that one line is here, one line is there, another line is here, another line is here, another line is here. So the answer is going to be z equals cos z equals cos 2 pi by 3 plus I sine 2 pi by 3. And here z equals cos 4 pi by 3 plus I sine 4 pi by 3 and z equals 1. Right, now a very important topic. So that's the graphical representation of the solutions. Complex conjugate root theorem. Complex conjugate root theorem. An import pattern has mirrors which can be very helpful in finding complex solution. Previously, we can see that the complex conjugate of solutions are also solutions. Complex conjugate root theorem says that if a polynomial with real coefficients has a solution a plus ib, then its complex conjugate a minus ib is definitely also must also be a solution. To the polynomial. This is a very useful result and can sometimes save a bit of time. Now, considering root theorem. Examples: x squared plus 2x. Example: 2x plus 5 equals 0 has the solution. x1 equals minus 1 plus 2i. Then x2 is definitely going to be minus 1 minus 2i. Then comes complex solutions. In general, we can solve the equation for Zn equals w by following steps. Expressing both sides of the equation in exponential form. R to the power n e power in theta equals w there, and e power I still don't know the theta naught I theta naught plus 2n pi 2 pi, okay, 2 pi k, same thing. And then equating the coefficients and exponents powers, you can see r equals w power 1 by n, and n theta equals theta naught plus 2 pi k. Okay. And the theta naught plus 2 pi k, calculating the n solution by substituting in k equals 0, 1, 2, 3, and so on. Find all the solutions for z cubed equals minus 2 minus 2i. Okay, so this is r equals root over 4 plus 4, 8 to root 2 is r. E power I theta, so e power I theta is minus minus, so it's in third quadrant, and pi plus pi by 4 is 5 pi by 4. I 5 pi by 4 equals uh, 1. Okay, I can't write 1 directly. So we're going to do, we've got till here, okay, but we need 3 solutions. Cube, right? Alright, z equals, okay, we need 3 solutions like that, plus 2 pi k. Alright, now we have to find solution. Left hand equal, look, z equals r e power I theta, z cube equals r cube e power I 3 theta, so z cube equals r cube e power I 3 theta equals 2 root 2 e power I 5 pi by 4 plus 2 pi k. If we compare that, alright, both of the exponential form, then we can find r equals 2 root 2 cube root and 3 theta equals one z solutions, and 3 theta equals 5 pi by 4 plus 2 pi k. K equals 0, 1, 2, 3. If k equals 0, 3 theta is going to be 5 pi by 4, theta 5 pi by 12. K equals 1, 3 theta equals 5 pi by 4 plus 2 pi. Theta equals 5 pi plus 8 pi. 5, 13 pi by 12, and k equals to another one. So you can see from here the cube root of 2 root 2, we find something, or we can say cube root of 8, right? Three by 2, 2 cube, and so it's going to do root 2, okay? It's going to be root 2. And theta equals 12 plus, okay, that. So the answers are pretty simple for k equals 0. For k equals 0, so 0 equals 2 e power I 5 pi by 12. Z1 equals root 2 e power I 5 pi by 12 plus 2 pi by 3, cosine 13 pi by 12, and k equals 2, z3 equals root 2 e power I 21 pi by 12. Okay, that's the solution. Okay, and cube root 2 root 2, right? So 2 power 1 by 3 into 2 power 1 by 6 equals 2 power 1 by 3 plus 1 by 6 equals 6. 2 plus 1, 3. 2 root 2. More importantly, we can easily get the cube root of 2. Cube root of 2 is cube root of 2. And root 2. It comes from root 8. Alright. 8 power yeah, it becomes r cube equals root 8, so r equals root 2 instantly. Right, okay. Root 2 e power I 5 by 12, 2 power I e power I 13 pi by 12, and root 2 e power I 30 pi by 12. These are the 3 solutions. And then the common solution. Not all equations have a finite set of solution. For example, what is the solution of the below equation? Z modulus equals 2, so z equals plus minus 2. Our solution, but are there more? To find all solutions, we must treat z as a complex number. Okay, we can treat z as a complex number. Remember then z plus minus 2. Then z equals x plus I y equals 2. Calculate the absolute value gives root over x squared plus y squared equals 2. X squared plus y squared equals 4, which is a circle use 2 minus 2. Okay, it's a circle. Therefore, solution z2 are numbers which satisfy this thing. Numbers which satisfy this thing. So or in other words, all complex numbers which lay in a circle of raised 2 centered at the origin. The set of solution is called the locus. Say of the solutions, set of solutions called locus. So every complex number with length 2, is solution 2. Z equals 2. And how do we show the complex numbers? Say here, 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 here. This one's a complex number. 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 It's 2, 2. Okay, all of them has got solution. Has got a solution of z equals 2. We can sketch the set of all solutions by simply drawing a circle of radius to center at the origin. Here, 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 here. That's it. That's 2, 2, and it's minus 2i. It's minus 2i. Similarly, if the equation was z is less than 2, the locus would include all complex numbers with lengths less than 2. That means if we draw the circle, the locus would be, the locus would go only from here till here, here till here, here till here, here till here. It wouldn't touch the radius. Alright, my touch, but it should be less than 2. Okay? Alright. Now we've got matrix. Revision on matrix. Okay? Revision on matrix. Again, well, it's okay. The topics we're going to cover in here is the arithmetic of matrices, transpose, trace, and determinant. So, a matrix is an array of numbers. So it can be this array of numbers. Okay. Oh, you can make several. Okay, it can make several forms. Oh, area eraser. Okay, so we can now see the matrix can be small, it can be rectangular, square, big, and different rows and columns. So this is the rows and this is the columns. We say R by C is the number. The dimensional matrix, the dimensions of a matrix are written as the dimension of a matrix are written as rows times columns. Right, and the entry I is the number of row and j is the number of column. And we can add and subtract matrix, and we can multiply, and matrix multiplication goes with row of matrix, the column of matrix, and we need to know about the matrix multiplication that AB is not equals B. That means it's not like normal multiplication. If you change the form, if you take A in first and then later on B in first, it's going to be different. AB is not going to be. Now, matrix transpose is when you turn the row into a column. Into the column. The first row is the first column, second row is the second column. And that's how, for example, we can use matrix transpose to construct a square matrix. Right? But A times A transpose is a square matrix. We can write that with A transpose. That's going to convert that into a square matrix. This means we can use the transpose to convert a system with no or infinite solutions to systems which can be solved using matrix inverses. So we can use transpose to convert the system with no solutions to a system which is solved using matrix inverses. Alright, so we can find the determinants. The determinants of a square matrix is a special number which tells us several useful properties about the matrix. Consider the matrix, square matrix A. We write the determinant of A as determinant of A, and the determinant for 2 by 2 matrices is to calculate if a matrix is A, B, C, D, then the determinant of A would be AD minus BC, and the inverse is going to be 1 by, this is AD minus BC, and this is DA minus C minus B. This is for the inverse of the square matrix of 2 by 2. So, matrix transpose can also be used to simplify the expression of matrix equation. For example, we can express a matrix equation can also be used to simplify the expression of matrix equation. For example, we can write X transpose and then A matrix and X in terms of matrices and their transposes equal, well, not quite, but transpose gives us a square matrix, and then the A really turns it into 0. So X transpose A X equals 0. This is another equation. And expand X transpose A X equal 0, where A is something, X is something, and trace. Say if we got a matrices A, B, C, D, E, F, G, H, I, then the trace of matrix A is going to be A plus E plus I. The trace is always a number. And then determinant, we can calculate the determinant of large matrices using cofactor expansion. Cofactor expansion. To do this, we must first select a new row or column, and if we choose the ith row, then the determinant is determinant of A equals summation K equals 1 to N A of I K into C of I K. If we choose the and the ith column, the determinant is determinant of A equals summation K equals 1 to n if ki c of ki. In that case, where Cij represents Cij. Now that we've come till this far, the next topic, say, where Cij represents cofactors. Calculate the determinants of A using first row. We choose I equals 1. I calculate the determinant of A using first row. Okay. There's a example 2, 1, 3, 4, 5, 6, 7, 8, 9. So, in the first row, it's gonna be 45 minus 48. Okay, minus. It's gonna be 36 minus 42 plus 3 into 32 minus 35 minus 6 plus 6 minus 9. Answer is minus 9. Different tricks. To the row and column, the most zeros, of course, is the most important. Each assignment is to remember the sign of the cofactor. Okay, now, upper triangular matrix is a square matrix where all elements below main diagonal are 0. So, A, B, C, D, E, F. Okay, something like this. In this case, the determinant of an upper triangular matrix is a product of the element on the main diagonal. So determinant of A is going to be, in this scenario, ADF, and then ABC, DAG, 0, 0, 0, and in this case, determinant of A equals ABC. Lower triangular matrices. A lower triangular matrices is a square matrix where all elements of the above the main diagonal are 0. So a 3 by 3 lower triangular matrix would look like A, B, C, D, E, G, 0, 0, 0. And the determinant of A is going to be A, B, C. A lower triangular matrix is a product of elements on the main diagonal. So, triangular matrices. In general, if A is an upper or lower triangular n by n matrix, then the determinant of them is a product of the diagonal entries. This is a very useful property. Matrix equation, matrix inverse systems. Now the two topics we're going to cover in the next one is the matrix equation Inverse of a matrix. Inverse of a matrix. So system of equations. Inverse of matrix. System of equation. We can use matrices to represent we can use matrices to represent system of equations. We can convert any system of equations into a matrix equation. For a general system of two equations, ax plus by equals s, cx plus dy equals t, right? A, b, c, d, x, y, s, t. Beat it down. Note, when you multiply this out, you get the system of equations you started with. For general system of m equations and n variables, the corresponding matrix is going to be like that. Ouch. One way to solve these equations was to apply elementary row operation in an augmented matrix until we reached reduced row echelon form, which is going to be, say, minus 3x minus 2y equals 1, and minus 3x plus 3y equals 3. Right, minus 3 minus 2 minus 3, 3x, y, 1, 3. And then if we do r1 plus r2 plus r1, then the r2 becomes, sure, oh, there's a minus, it's plus, that's correct. R2 becomes 0, 3 minus 2 is 1, and here comes 1, 3, is 4, and 3 minus 2 is 1, 4, right? And r1 plus 2r2, and then it's 2r2 0, plus 8, 9, 4, 1, 0, and came to this formula. Oh, what's going on? 2r2, and then if we do 1 by 3 into r1, then we get 1, 0, 3, 0, 1, 4, and later we get x equals 3, y equals 4. From here, x equals 3, y equals 4. Now, system of equations. The elementary row operations we can perform are adding or subtracting a multiple of one row from another row, interchanging two rows, multiplying all, then adding or subtracting a multiple of one row from another row, Okay, and interchanging of two rows, which is gonna be like multiplying all entries in a row by and multiplying all entries in a row by a non-zero constant. In a row by a non-zero constant, we can do that. We perform these operations until the matrix contains pivot. First non-zero. We perform these operations until the matrix contains pivot. In each column. A pivot is the first non-zero. And what is a pivot? Okay, I show an example. So say 5, 4, 3, 0, 0, 0, 0, 0, 0, 0. And what are the pivots? With a different color. And make a proper circle, 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 pivots. We perform these operations until the matrix contains pivot. Alright, so we continue to perform these operations until the matrix is reduced row echelon form, where from which point, what is the row echelon? From which point you can't do the row operation anymore, so it's maximum point. If you do more, then the matrix is not going to be the, see, now it's almost, you have only diagonal matrix, and that's your determinant, which is 60. But if you have 1 more 0, that's not, we can't make more zeros, and that's how this is the row echelon form. If you couldn't make more zeros, then the determinant value would also change. So this is the final row reduced form of the matrix. We continue to perform this. So we've got the row reduced echelon form. We say that we continue to perform these operations until the matrix is in reduced row echelon form, which means the pivot in each row is on the right of the pivot in the above row. All 0 rows are at the bottom of the augment matrix. All the pivot entries are 1. Each column which contains a pivot has zeros everywhere else. Entries are 1. So reduced row echelon form is gonna be 1 1 1 0 0 0 0 0 0, and you can add something in here, which is going to be the value. Okay, so that's the reduced row echelon form. Okay, reduced row echelon form. Now, once we finish the reduced row echelon, to solve the matrices with the sequence system of equations, we find it. If it's 1 1 1 0 0 0 0 0 0 and there's a 503 in here, so x equals 5, y equals 0, z equals 3. Matrices. Okay, to solve a system of equations which has infinitely many solutions, we treat one of the unknowns as free variables. We treat one of the unknowns as free variable. So we have to remember this term, free variable. A free variable are unknowns that correspond to columns which contain no pivots. Which means, in this case, we can write 5, 0, 2, 0, 0, 1, 0, 0, 0, and still we can make a very perfect solution. In this case, we're going to make 5, 0, 0. So in this case, look at this. This is x2 is a free variable. And sometimes the column which contain no pivots. Again, you have to remember, free variables are unknowns that correspond to columns which contain no pivots. So here, x is a free variable. There are different cases. There are different free variables. Let's show one more example. Say and 0, 0, 0, 1, 0, 0, 2, 1, 0, 5, 0, 0. And we can say this one, x1 is a free variable. Okay? And we can take another one. 1, 2, 4, 2, 0, 1, 2, 1. There's a gap in the middle. And the box that shows this is a free variable. Okay. So from here we go to the matrix equation. We thought that we could solve this system of equations by reducing the system to row echelon form. However, if there are many equations variable, this process could take a while. In that case, if we continue, we can introduce a new notation to make writing these equations easier. We can say this is the matrix, this is the variables, and this is the solution equals B. There are several notations to simplify matrix equation in mathematics. They write x equals b in here, engineering or physics, x equals b goes in the vector form, and textbooks and type notes is like this, a little bit bold. So now that the matrix equation has a simpler form, we can focus on solving it. Ax equals b, so x equals A inverse b. It's a pretty good solution for the matrices, and teach that A is a matrix. So what's A inverse? A inverse is the inverse matrix. Inverse matrix of A A's inverse is the multiplicative inverse of the matrix A. So similar to numbers, A inverse equals 1. Matrix inverse multiplication would give you an identity matrix, where I represents the identity matrix. Matrices, matrix equations. The antimatrix is a square matrix with ones on the main diagonal and zeros elsewhere. The size of the antimatrix depends on the dimensions of the matrices you're working with. So I2 is going to be 1, 1, 0, 0. I3, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0 is actually 1. And I4 is going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1. Okay, we're not supposed to do that. And then comes some figuring out. There it is. That's I2, I3, and that's I4. Multiplication of matrix by identity matrix results in no change. That means I sub n times A equals A, and A I sub n equals A. What means A into A matrix, A multiplied A inverse equals IN. If you can't find A inverse, then solving the matrix equation is simply a matter of matrix multiplication. X equals A inverse. But you still need to actually calculate A inverse. Finding the inverse of a 2 by 2 matrix is easy. A equals A, B, C, D. A inverse equals 1 by AD minus BC. It's D, it's A, it's minus B, it's minus C. Note this only works for 2 by 2 matrices, where AD minus BC is not equal to 0, and AD minus BC can be 0. Alright, finding the inverse is a little trickier for larger matrices. Let's find the inverse of this one. 1, 1, 1, 1 minus 1, 1, 0, 0, 1. we just make it a very good form. And then we can do this by augmenting our matrices. Our matrix A with identity matrix I3. So this is A, and then we're augmenting it 0 0 0 1 0 0 0 1. Okay, this is I3. This is A. I3, and I'm going to go by row reducing the augmented matrix. We'll encode all our row operations. So at first we can go R2 minus R1 and we get 0 here, minus 2, 0, minus 1, 1, 0. The rest are quite similar, quite same. 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1. Let's put something in here. And make it a proper matrix. Yep. That's almost done. Not almost, actually. We just did what I did in here. R2 minus R1. And then we can do from here, from the previous one, minus half R2. We get 0, 1, 0, half, minus half, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1. And from there, we can go R1 minus R2. R1 minus R2 is gonna be 1, 0, 1, half, half, 0, 0, 1, 0, half minus half, 0, 0, 0, 1, 0, 0, 1. And from there, you almost got something. So, now we have come to a point okay, R1 minus R3, then we can put minus R3 gives us 1, 0, 0, half, half, minus 1, 0, 1, 0, half, minus half, 0, 0, 0, 1, 0, 0, 1. And then from there, we can say, again, let's make it a little bit good form. And from there we say, now this became I3 into matrix, and this became our A inverse. See? It used to be A I3. If I3 comes here, this becomes the A inverse. So, we got our A inverse already. There are matrices which do not have inverse. For example, when the determinant is 0, we cannot do the inverse. Okay? They do not have the inverse. And matrices with no inverse, say, an example, -2, 2, -1, 1. In here, determinant of A equals -2 plus 2 equals 0. And A inverse goes to 1 by -2 plus 2, which is 0. And we change that 1 minus 2 1. But we know it's not going to work. There is something in here, so there is no inverse. Matrices with no inverse correspond to inconsistent. Alrighty, I got a little bit inconsistent system. Well, there's a bit gap we see. For example, consider B equals 1 1 1 0 1 1 0 1 1. Okay, we do this one. Then we do this 1 1 1 1 0 0 0 1 1 0 0 1 1. Then we do R1 minus R2. It's gonna be 1 0 0 1 minus 1 0 and R3 minus R2. You get 0 0 0 0 minus 1 1. In here 0 1 1 0 1 0. The augment matrix shows us the issue in here there are 3 zeros together, which is not supposed to be there. Matrix with we have to be careful when manipulating matrix equation. Okay, and in general, AB is not equal BA. AB is not equal BA for matrices. A and B. However, we can multiply an equation by a matrix on the left. So AX equals B, then A inverse A into X equals A inverse B. In that case, X becomes A inverse B. Some properties of inverse. AB inverse equals B inverse A inverse. A inverse inverse equals A. KA inverse equals K inverse A inverse, where K represents a constant. K inverse A inverse, where K represents a constant. Matrix determinant and inverse. Determinant and inverse. The most useful properties of a determinant are, if determinant of A is not equal to 0, then A is invertible. But if determinant of A equals 0, then A is not invertible. Then we move to the next properties. Properties of non-invertible matrices. The below statements are all equivalent. If one is true, then they all are. For non-invertible matrices, A isn't not invertible, which means the exact same thing. Doesn't make sense. A can be reduced to the identity matrix. Identity matrix. IN by performing elementary row operations. Meaning elementary row operation. At least one of A's rows can be reduced into into a zero row by performing elementary row operations, and for determinant of A equals 0. One is correct, then all are. Properties of invertible matrices. Oh. What? A is invertible, and A can be reduced. It's just the opposite of the non-invertible. It can be reduced to the identity matrix by performing an operation. The 3 is the system of equation represented by x equals 0 has only the trivial solution x equals 0. And here it says the system of equation represented by ax equals 0 has only one trivial solution, which is x equals 0. Number 4, the system of equation represented by x equals b has a solution for every vector b. Okay. And determinant of A is not equal to 0. It's the major thing, most primary thing. Then we come to vector spaces. The topics in here: sets of vectors, linear combinations, linear combination, linear dependence, and linear independence. Now, revision says vector spaces. Sets are widely used all throughout mathematics. The following definition of a set is due to the father of set theory, who looks a bit like And yeah, looks a bit like it. Okay. Looks a bit like this. His name is George. Cantor. He didn't have much hair. Otherwise, I'd definitely give it. Yeah, that's the most amount of hair. George Cantor. So, definition. He had given a set is a gathering together into a whole of definite, distinct objects of our perception or our thought, which are called elements of the set. Okay, so gathering together into a whole of definite, into a whole of definite distinct objects of our distinct objects of our perception or our thought, which are called elements of sets. Now, vector spaces. So that's a pretty good definition given by Mr. George. And that's what set is. Set is like a box where you put your things and all the elements together form the set. In plain words, there's a collections. This is going on a revision on sets. Collection on sets. So there's collections of objects like we humans are able to think together as a single entity. A good analogy is to think of sets as abstract bags or boxes in our mind, then hold the elements together. That hold the element together. Okay. There's our box. We put all the things in. As you can see, thing can be an element of a set. We can put anything inside the box, and anything can be an element. To communicate effectively, sets are written with a specific notation. Elements are listed separated by commas, and the list enclosed between braces. So, we all know what it is. The set A is a set of numbers. Example X is a set of letters. Y is a set of shapes, square and triangles. This is a set of vectors. So, set of vectors is going to look like this. Z equals, say there are vectors like this. 1, 3, of course, by commas separated through -1. And there's a curly brackets. That is a set of vectors. Vector spaces. We can state that an element belongs to a set using the membership symbol. Element. If, for example, S equals 95, then 5 element of S. S5 is an element of set S, or shortly S5 is an S. 5 is an S. We can also use element to select an element contained within a set. For example, X in here we can write X element of Z. So X could be this, and you can write or this. We can use another notation to define more complicated sets, usually, but not necessarily, those having an infinite amount of elements. The set of positive real numbers. Okay, it's gonna be something like this. All real numbers. X element of R augmented with X greater than 0. This is such that and other vector forms. The set of integers between 1 and 5 inclusive. So it's going to be 1, 2, 3, 4, 5 equals X element of Z such that X 1 to 5 1 to 5 inclusive. We will focus on sets whose elements are vectors. Recall that we will focus on sets whose elements are vectors. Recall that R denotes the set of all real numbers. R squared denotes the set of all two-dimensional vectors. So we can write element of, it's almost like R squared, and R cubed denotes the set of all three-dimensional vectors. Can be 2 sine 3 ln 2 element of R cubed. We can build other sets that have a few vectors or a lot of vectors. We can give them any name too, but we often use capital letters. Example, a set with 3 two-dimensional vectors. It's gonna be 1, 2, 3, 4, 5, 6. Okay. A set with all two-dimensional vectors whose first coordinate equals 4. So it's going to be like B equals xy element of R squared as if x equals 4. And then the set with all three-dimensional vectors, find the button below. Okay. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. and so on. For the vectors that contain the set below, c equals 0, so every time c equals 0, it can be there. Vector spaces, linear combinations. Linear combination and what is this? Linear combination. Linear combination of vectors are a special way in which we write vectors. Linear combinations can only be formed using the operations adding or subtracting of vectors, multiplication of vectors by scalars. Linear combination. Definition. Linear combination a linear combination of the vectors v1, v2, v3, vn, element of Rn. Is a vector v of the form v equals c1 v1 plus c to v2, these are the vectors, plus c3 v3 plus ck vk. Scalars. Say the vectors are in a set b equals v1, v2, v3, v4. We also say that v is a linear combination of the vectors. Right, we also say that v is a linear combination of the vectors in B. The real numbers c1, c2, and c3 are called the coefficients of the weights of the linear combination. The coefficients of the weights of the linear combination. Let's give an example of linear combination. Let's take the vectors v1 equals 1, 0, 0, and v2 equals 0, 5, 0. To build a linear combination v1 and v2, we are free to choose any scalars. Choosing to build a linear combination of v1 and v2, choose any scalars. Choosing 4 and 3 in that order. That means 4v1 plus 3v2 is going to give us 4, 5, 0. Not exactly. 4, 5, 0. That's 4, that's 15, and that's 0. A linear combination of v1 and v2. Linear combination. Vector space. Okay, let us take the vector v1 and v2. If we choose other scalars like 1 and minus 2, we get a different linear combination, okay? I go 1 minus 2, 1v1 minus 2v2 is going to be 1 minus 10, 0, another linear combination. And the linear combination. V and V2. Vector spaces. And the linear combination. Now comes the vector spaces. It is important to determine when a vector can be written as a linear combination of a given set of vectors, and if so, how. The answer usually reduces to solve a system of linear equations. Example, write v equals 3 minus 1 as a linear combination of the vectors v1 equals 1, 0, and v2 equals 2, 1. So if we do 6v1, not 6 minus 2, it's not 5v1, it's gonna wait a bit. v1, okay. 5v1 minus v2 is going to get 3 and here minus 1. That's it. We got it. Now, we must find scalar C1 and C2 such that v equals C1, v1 plus C2, v2. So it writes like that. It goes there. And we bring 3 minus 1 here. And then we find it. Another way, is there a 2 in there? Five, 0. Two minus 1. Correct, we are correct. So if you put things in there, then there we can write C plus 2, C2 equals 3, and C2 equals minus 1. So the combination of 5v1 minus v2. Alright, so find scalars using the linear combination. V equals C1 v1 plus C2 v2. And then U equals C1 U1 plus C2 U2. If it's a like 3-dimensional vector and got 3 vectors, 3 scalars, and turns to U, then you can also write equals C1 U1 C2 U2 C3 U3, and you can find it out the same way. This is a linear combination of vectors. Suppose you are given V a vector and B a set of vectors. V a vector and B equals V1 VK, a set of vectors. A natural question to ask is it possible to write V as a linear combination of the... Is it possible to write V as a linear combination of the vectors in B? So you're going to be a vector of... The answer is not always. Not always. It depends on the value of v and what vectors are in the set v. V is linear combination of vectors in is it possible to write v equals 1, 0? Says, is it possible to write v 1, 0 as a linear combination of vectors b 0, 2, 0, minus 4? I don't think, because it doesn't matter how much you multiply 0, it's always going to be 0, and the addition and subtraction is going to be same. And then comes, okay, is it possible to write with 0, 2, 1, 2? Definitely. You just subtract from this one, and you get 1, 0. So it is important to distinguish when a vector v can be written as a linear combination of other vectors in a set. V equals v1, vk. In fact, when v equals 7, v1 plus v2 plus 3, we can also write the 0 vector 0 as a linear combination of vectors in the set v, v1 to vk by rearranging 0 equals cv with c equals minus 1. In fact, when v equals all these things, we can also write the 0 vector as a linear combination of vectors instead of just this. So it's going to be cv plus c1 v1 plus c2 v2 plus ck vk equals 0 with c equals minus 1. V equals c1 v1 plus c2 v2 c3 v3 plus ck vk. In that case, that's how it works. A set of vectors b, v1 to vk is linearly dependent if we can write the 0 vector as a linear combination if you can write the 0 vector as a linear combination of vectors in B with at least one coefficient different than 0. Okay, so this is vectors equals is linearly dependent if we can write the 0 vector as a linear combination of vectors B with at least one coefficient different 0. Okay, a set of vectors is linearly dependent if we can write this. A set is linearly independent exactly when it is not linearly dependent. For more explicitly, a set of vectors is linearly independent if there is no way to write the 0 vector as a linear combination of vectors in B with at least one coefficient. Okay, so there's a way you can write those as a linear combination, and that's how it's different. should be linearly independent. So set minus here, then all the vectors going to be 0, 0, 0. We need to show that the 0 vector is a linear combination of the and b, and this means that if we set up an equation like this, 1, 0 minus 1, and c0 minus 1, the equation becomes true. This one minus. Therefore, B is a linear independent set. When finding a solution by inspecting is not easy, you can follow steps 1, 2, 3 used in the next example. Alright, so 1, 0, 1, 1, 0, 0, 0, 0, 1. Here's with minus here, minus 1 in plus plus, you'll get 0. Or minus here and here, still get the linear independent set. Vector spaces show that the set B is linearly independent. So it's 0, 1, 0. Minus 1, 2, 2, and minus 1, 1, 1, 1. So it's like a vector. Gotta find C0, C3, 0, 0, 0. In that way, or we could use this one, C1, C2, this one, C3, this one, equal this. We need to show that the 0 vector is not a linear combination of the vectors in B. In other words, if we set up the equation like this, equation that R0 equals 0. Find that all coefficients are 0. It's the only way. In other words, the only solution is the trivial solution. Only solution is a trivial solution. In that case, is linearly independent. Express trivial solution linearly independent. Express the system as a matrix equation. Express the system as a matrix equation. you'll feel better. In that case, row reduced augmented matrix. R2 minus R3 and R1 plus R3, and then R3 minus, didn't find it. Solve the system. C2 equals 0, C3 equals 0, C1 equals 0. So C1, C2, hey there, equals 0. Therefore, the vectors in the set B, vectors in set B are linearly independent. Linearly independent. Now, determine whether the sets of vectors below are linearly dependent or independent. Well, A is linearly C1, C3, and we can do this in a form to make it 0. What? You find it the same way. And the final section to determine whether this vector below linearly dependent or independent. Finally, do the row echelon form. C1 and C2, C3 is not equal, then you got it. And whether the sets of vectors below are linearly dependent or independent. Form C3 to get the pivot on. C1 plus into U3 where 1, 0, 2, 0, minus 1, 3, 2, 0, 4, and all the values of K linearly independent. It's definitely going to be independent. Let's make it that way. And then there comes the topic of vector spaces span of a set of vectors. Span of a set of vectors. So, definition. A vector space V over R consists of, I said V, the elements of V are called vectors, and addition operation between vectors for V W element of V, element of V, then V plus W element of V. V for lambda element of R and V element of V for lambda element of R and V element of V. Okay, right. Lambda V element of V. Okay. Definition: a vector space contra. A vector space VR consists of a set and additional and scaling multiplication satisfying the properties below. An addition and scaling multiplication satisfying the properties below for vectors V, W, U, element of V, and scalars lambda operate. And scalars lambda mu element of R vector 0 V 0 plus equals U lambda equals V lambda equals V. The Euclidean vector space. The Euclidean vector space. V1, V2 plus W1, W2, V1 plus W1, V2 plus W2, of course. Scalar multiplication lambda, then lambda is multiplied. The Euclidean vector space R cubed, the set of all three-dimensional vectors, is a vector space. Okay. The Euclidean vector space R cubed is a set of all three-dimensional vectors in a vector space. Right, addition scalar. In a vector space is similar R to N, the set of all n-dimensional vectors in a vector space. Addition, scalar multiplication, and scalar multiplication. A vector space into the set of all matrices is a vector space. Addition, matrices. A vector space of polynomials, P2, is a set of all polynomials Px of degree less than or equal to 2, plus a1x plus a2x squared with a0 a1 a2 element R, addition, scalar multiplication. From now on, the word vector means element of a vector space. Okay. Of a vector space. Element of a vector space. And not only the vectors we are used to. element of a vector space, and not only the vectors we are used to. Vector space, and not only the vectors we are used to. Vector spaces, even a set of vectors B in a vector space V, we can build a new set of vectors formed by all possible linear combinations of vectors in B. This new set is called the span of B. It's called spans. We're already here. This new set is called new set is called the span of B. The span of a sector, the span of a set of vectors B equals the span of a set of vectors B equals V1 to Vk is a set of all linear combinations of vectors in B. So span of B equals V element of V equals C1 V1 plus C2 V2 plus C3 V3 CK VK with C1 C2 element of R CK. Vector spaces in the span of a set of vectors B equals V1 to Vk is a set of all linear combinations of vectors in B. Combination of vectors in B. Span of B equals, let's write it. Let us consider a set with only one vector in R square. B equals 1, 2. To calculate the span of B, we need to find all linear combinations of vectors in B, but since B only has one vector, linear combinations have the form only has one vector, V equals C1, 2, C to C. Definition: the span of a set of vectors B equals V1 to Vk is a set of all linear combinations in vectors in B. Span B equals V1 to V equals C1 to C1 V1 to Vk. Therefore, span of B equals C to C. So span of B equals C to C um, element C element R. C element R. This is a set of all constant multiples of the vector this is a set of all constant multiples of the vectors 1, 2 in R. Geometrically, this is the set of points in the line of slope. This is a set of points in the line with slope to passing. And geometrically, this is the set of points in the line in the slope to passing through the origin. Calculate the span of the set B that has only one vector in R cube. How does set span B look like within R cube? Which set is spanned by the set of vectors below? Span A, the element square, V equals C1 this, C2 this, C1 C2, C1 C2 out of R equals R squared. Spanned by the set of vectors below. Find the span of the following set of vectors. What vector spans the set below? B equals 0. Find a set such that S equals span. First, let us consider a general vector V in S. Now, span B is independent. Okay. A equals 2, B equals 0, this is subspace. In the third condition, 0 vector is 0. We conclude that S contains a 0 vector. Should the set below is subspace of R cube, we must check that the result of adding any two vectors in S is also in S. Let U V element of S, U plus V element of S is closed under addition. Show that the set below is subspace of R cube. Scalar multiplication must check that the result of multiplying any vector in S by scalar is also in S. And V element of S and C element of R, then CV equals C into this of S. Therefore S is closed under scalar multiplication. S equals this element of R cube, C element of 0. Since we have shown that the set S contains a 0 vector, is closed under addition, is closed under scalar multiplication. closed under addition and is closed under scalar multiplication, you can deduce that S is a subspace of this one. The total subspace R3 is a subspace of R3. Indeed, the zero vector of R3 is in R3, addition of vectors in R3 stays in R3, and scalar vector in R3 stays in R cube. Therefore, R cube is a subspace of cube. Furthermore, there is nothing special about cube in this example. In fact, for any vector space V, it is true that V is a subspace of V. Show the sense below the subspace of R cube. Basis. An interesting fact is that span is always a subspace of Rn, regardless of what vectors of Rn are in the set B. Indeed, the zero vector is always a linear combination. Just take all coefficients to be zero. The sum of two linear combinations of vectors in B is a linear combination of vectors in B. You just rearrange to get the sum of the coefficients. Scalar multiple of a linear combination of vectors in B is a linear combination of vectors in B. Just multiply all coefficients by scalar. All subspaces WRN can be written as span B for some set B. W equals span B with B equals W. This description, despite being true, is not very useful. Our goal is to find a set B as small as possible that spans the subspace W. We call this kind of set basis. A basis, a subspace W of Rn, is a set B, W1, W2, Wk of vectors, Wi equals element of W, that has the following two properties. W equals span B. B is a linearly independent set 1 0 0 1 xy x 1 0 y 0 1 a cube like that, P2 P3 M2 by 2 standard basis vector is a linear combination of the standard basis. Combination of the standard basis. A plus B plus C plus D. Standard base for Rn. The standard base for Rn. So the standard base for Rn is En. Show that the set below is the base of R's. First, you must show that B is a linearly independent set. Next, you must show that the span of B is R square. And show that the set below is the base of R square. We must show that C1 plus C2 equals 0 if and only if C1 equals C2 equals 0. We turn the equation into a matrix equation with its augmented matrix. 1 1 C1 C2. Show that the set below is the base of R square. Applying row operation gives R plus R2 blah blah. C1 equals C2 equals. So B is a linear independent set. Independent set. Okay. And show the set below is the basis of R square. B spans subspace R square of R square. Span B equals span B span 1 minus 1 C1 plus C2 C1 C2 into R C1 C2 C1 plus C2 R B1 B2 element of R. Since the set below is the basis of R square, B equals 1 1 minus 1 1 Since the vectors in B are linearly independent and span B equals R squared, the set 1, 1 minus 1, 1 is a base of R squared. So the sets below form a basis for R squared and cube respectively. Sets below form a basis for cube respectively. 1. Determine a basis for the subspace W of R cube below. XY is the element of R cube. Determine a basis for the subspace W of R cube below. A child vector V in W. Split 2 days. 2 days also make a difference. Very big difference. And W has a form. W equals x plus y z. Z y z y 1 1 plus z 1 0 1. Span 1 1 0 1 0 1. Basis for subspace W of R cube. Subspace of W of R cube below. General vector V and W has a form. Shows that W equals span. Basis for the subspace W of R cube below. So Z element of R cube. Vectors are not multiples of one another. They are linearly independent, and therefore they form a basis of W. Because 1 1 0 1 0 1. Which are in groups. Of R cube. Of R cube. Below individually in group. Given a basis of the subspaces of R cube below. And x equals minus z. And W4 equals x y z element of R cube. It's 2 element of 3z. The numbers of vectors in a basis of a subspace W is called the dimension of W. The dimension of subspace W equals x y z R cube. X equals y plus z. Contained two vectors shown only to determine the dimension of the subspace. Okay, below other properties of subspace are in bases. The subspace can have infinitely many different bases. Any two bases of subspace will contain the same number of vectors if the dimension of a subspace W is k. And then any set of vectors, any set more than k vectors from W is linearly dependent. Any set of less than k vectors from W will not span W.